The Tiger Beetle Sessions, Session 6, Wednesday, 12th of January 2022. Happy New Year, Isaac.
Happy New Year, Lauren, and welcome back, everybody. Um, when we left off, we were working on our in-memory representation for our LSM trees and our LSM forest, and figuring out how to efficiently query or efficiently build an in-memory index of where tables are on disk. And tables are where the data is actually stored in the LSM tree. So we need a way to go quickly from a key to then a table location on disk. Because we want to address lots of storage, we have a very big manifest potentially in memory. And so, you want to remind us of some of the strategies we've been using to optimize this query path, Yaron?
Yeah,
Uh,
thanks. I'm glad you did the overview because I've been trying to remember where we ended off. I knew it was manifest, but uh, yeah. So we've got a whole lot of these tables on disk, maybe up to 2 million if you want to address like a whole lot of storage. If you want to address up to like we're thinking of a very high limit, which is then the hard limit, maybe 100 terabytes or something, which is crazy. But then we design everything, check the back of the envelope numbers, and make sure that we can scale up to there without the design falling apart. And then beyond that, maybe we would have to change the design a little bit more, like the Jeff Dean 10 times rule. Design 10 times bigger than you need to be. And then if you go beyond that, then you maybe need a new design. So yeah, 2 million tables. We need to track the metadata about those tables. It's about 64 bytes of metadata per table. So 64 times 2 million. Some of the challenges of tracking all this metadata is that we have to do static allocation. So we don't, once Tiger Beetle is running, we don't want to do any malloc calls because malloc can fail, and we want to make sure that when Tiger Beetle starts, it can't fail. So it's got everything it needs. It also makes things faster because we don't need to, we've got our memory that we need all acquired up front. Uh, but the static allocation makes it a little bit challenging because also we've got this LSM forest. So the LSM forest is lots of little trees because we love LSM trees so much. We don't just have one in Tiger Beetle, we have like 30. Uh, so we're making the LSM tree cheaper, more efficient, smaller. And if you can do that, then you can have many of them because the cost of them is cheaper. And if you can have many of them, then it's great because you can split your different data types. Each data type can have its own LSM tree, which means your queries become super fast because you know exactly where to go for certain types of data, and you exploiting the different characteristics of the actual data distribution much better. If you lump everything into a single tree, on the one hand, you only have the overhead of a single tree or the bookkeeping overhead. But the downside is now you've got all your data lumped in. It's not organized nicely. So,
yeah.
but now static allocation, we've got to allocate all the memory we need for the whole forest. Each tree needs to have its own memory, but we don't know in advance what the ratio between the trees is going to be. So we don't know, who's going to be the big oak tree, who's going to be the tiny sapling. That we don't know. So we can't just allocate every tree the maximum because then we would be wasting times 30. Because maybe only one or two trees are going to be really big redwoods, and the others are going to be tiny little bushes.
Yep.
Yeah, so basically we've solved this problem where we've got a static allocation pool that's shared by all the trees, like the water table under the ground. All the trees can tap into it, and they just suck out as much as they need. Uh, um, and so we've used the same idea for the manifest metadata. So we allocate like big little chunks of memory for each little um, to basically to store table metadata in. And then as the LSM tree manifest needs to grow, we're pulling more from the pool. And then the challenge after that was, okay, we've got, say one of the trees is like a redwood, it's pretty big. Now we need to find a table quickly. So I want, I need to do a lookup for a given key because this is like a key value store. So the key is ABC, and I need to know the LSM table that might contain this key. Now there's 2 million of them, so we've got to solve this problem really efficiently. So for each table, we've got a min key, and a max key in the metadata. So this problem is basically, to solve it, we have to look at all the tables, check the needle that we're looking for in the haystack is that key within the table's min and max key. So ABC is it between DEF and HIJ? No, it isn't, so it's not in that table. So it's this problem. So we can't just do like a linear search across 2 million tables metadata. That's too slow. So we have to do something like a binary search. Then we've gone beyond, we can't just allocate the metadatas individually because there's too much pointer chasing. 64-byte nodes, and you're linking them together like a linked list. It's too much pointer chasing. So we're grouping metadatas together into like nodes of something called an unrolled linked list, which is basically the foundation. And then we've got a little bit of binary search index. So we have like a root node, and we put the min key of each node in there. That links to more nodes, and that is where my memory ends. I think.
That's about where my memory ends too. I think we need to
Yeah,
get back into the details by looking at what we wrote
yeah,
up last time in that spreadsheet, and then what we've started programming. Because I think we ended up writing all the data structures out in the code last time when we left off.
yeah,
And we were then like actually getting into the then functions, implementing the lookups and whatnot.
yeah,
So
yeah.
I think when you're
But
ready, I'm ready to go look at that code and see where we can pick up.
yeah, yeah, I'm ready. Also, by the way, the YouTube or the session, Tiger Beetle sessions from end of last year, where we actually did all this manifest design work going back and forwards, Itzinger layout, linked lists, B plus tree, generic, like a fixed size B plus tree, and then finally this design that we've got now. All of that is now on YouTube. So
Awesome.
there's a new Tiger Beetle YouTube channel, and there's a different beetle there. So if you're on Twitch, then you'll see Performance Beetle, the rock star with the wings. If you're on YouTube, you're going to see something a bit more kind of blue. Anyway, it's looking nice up there. So
Cool. All
we're
right.
good to go. Yeah, let's jump into the code.
Share my screen then. We'll see if that works again. Okay. Yeah. It actually seems to work better in Chromium. Oh no, Discord still makes me click twice. So that is a Discord bug then.
Okay. Oh no, I was hoping you weren't going to mention Chromium at all.
Yeah. My mistake.
No worries. Yeah, so
All
we,
right.
we had
Anyhow,
some tech teething issues just before we started the stream. Firefox, Chrome, trying to get
yeah,
the
either it's a
stream.
Firefox bug or a River bug. I'm not sure which yet, but
Uh,
something was going wrong with the pop-ups. They were like supposed to let me select whether I just share the screen or not, or
yeah,
give permissions for the audio or video. So
yeah,
I'll look into that sometime
cool.
soon. But for now, we've got to use Chromium, sadly. Anyhow, what do we call this? This is like manifest level. This seems right. Is that a good size?
Yeah, yeah, this is perfect. Thanks.
Cool. Yeah, so we've got some code in here already, and we've got, looks like all our data is right here, it seems. Okay, so what do we have here? We've got the key nodes and table nodes. And so key nodes are then the index nodes. Essentially, they kind of give us index a table node, right? Yeah.
Yeah, yeah,
And then table nodes obviously contain pointers to table info directly, it seems. No, they just contain the table info directly.
yeah,
So we're not doing structured arrays here yet, but I think that was our plan was just to do it like this for now, and then if we actually see it's necessary, then optimize that later. Keep the code simple for us for the first implementation round.
yeah. I think we
Structure,
realized I think we tried out a little bit, like we ventured into structured arrays for the actual table info, but we realized we didn't need it because we needed we needed the keys to be structured arrays, which we've got in our keynode index.
right?
And then but then once we've done the key lookup, we actually want all the table infos to be grouped together. But I don't know if there was another reason that it was nicer to keep it together. Because we
Maybe,
did actually.
yeah, we did think about that, I'm pretty sure, but maybe we should just leave it, maybe we should just trust our past selves and leave it like this for now.
Yeah,
If we do
abs
decide to change it, it's just like a bit of boilerplate every time we use it to then switch around the field names or whatever. Um, this seems reasonable though. Um, table node count. Yes, then we index into this array of tables. So we do have an array of arrays of pointers sometimes. We were talking about 32-bit support, and we were saying we didn't really have arrays of pointers anywhere, but we do have one here and here. But
yeah.
let's see, what is this table node's max value? This is calculated here, it seems.
Really nice
Yeah,
comments.
yeah, I'm glad we did this.
Yeah,
We did leave ourselves a to-do here to come back and check about this -1 or this +1.
yeah,
Um, so that's a question more about the growth factor of a segmented array or segmented unrolled linked list, and if we need to round up here or not.
yeah,
Um, because we also are using div seal, so I'm not sure what the um, what the deal is there. I think that's not relevant to the algorithm though, so we were planning on coming back to that after we had kind of gotten things working. Because this +1 won't hurt us. It'll just maybe waste a tiny bit of memory in some cases.
yeah.
Um, cool. To do table node counts. Oh yeah, so we also, yeah, so we've got, maybe we should try and maybe like read through the lookup path again to see how we get from the key down to the table info. So we think we start um, just iterating over key nodes and like comparing, because each key node's got just an array of keys essentially.
Yeah.
So we've got the keynode keyman first of all. So then we kind of skip to the keynode. We can like do like binary search on the keynodes first of all.
Yeah.
Um,
So a keynote just contains a bunch of keys.
yep. Keys
And
and then indexes. Well, it's also got an keynode keymin table node. And then this takes us to the table node. It's the table node index then I believe. Um, you know,
yeah.
hmm, node pointer. I feel like it might be kind of nice to use like a type def here for a table, but maybe that's like going overboard. This is a table index though.
Yeah.
You might want to document that.
Yeah.
Or table node index.
Yeah.
Or maybe even better, like array of table node indexes.
Yeah.
Because this is an index into both like this array and this array and this array.
Yeah.
Um,
Isaac, can we check up top that we plugged in our actual block size for one of these nodes? Did we a node size? Okay, we've got it.
so we've
And
got also manifest node size. Then we've got key node capacity, which that's the number of keys that fit in the node size. And then that gives us the number of keynodes maximum. And this is the same thing for table nodes, essentially.
yeah. And can we just check that div seal in keynotes max? I just so I
Yes.
understand better the table count max. So shall we check out our config just so we've got concrete ideas in mind for like what node size is
Ooh,
and
this is compute
um,
table count max.
oh, cool.
Um, because this like rounds up to the next. This is the okay, so this is the maximum table size at as the first 7 levels. This kind of computes it for the number of levels we have and the growth factor we have.
Yeah,
This is going to be like our close to our 2 million number, but maybe not actually 2 million. I think we ended up going a bit less than that because it made more sense to the growth factor.
yeah,
2 million doesn't like fit evenly into like a power of 2 or power of 10 growth factor.
yeah,
You can end up like 1,100,000 or something like that.
yeah. Here's a curveball. I'm wondering our compute table count, that function, I'm wondering if that is correct because we were thinking of tables in the lowest level being bigger in size. So we'll actually have less tables in the lowest level, but they'll be bigger.
Does that
Or,
really affect the table count? Um, hmm.
yeah, although I don't know if it works the other way, if we're not just assuming that, because each level, so we've got level 0, which is small, then level 1 is bigger, level 2 is bigger, um, but it's bigger not in terms of the number of tables, but the actual data size. So um, if it was more, if it was just a simple LSM tree, you would have, say, in level 0, you'd have 10 tables and they're each 1 meg. In level 1, you'll have 100 tables and they're each 1 meg. And so,
Okay.
but
Right.
it's also acceptable for level 1 to have 50 tables that are 2 meg. And I think our function doesn't take that into account.
I think you're right. Yeah. I think if our function was correct though, this code here would work correctly. Is that right? It's a
Yeah,
table
yeah.
count max function. So I think
It
it's a
doesn't
bug that's not part
elsewhere.
of this code.
No.
Um,
Yeah.
so maybe our design changes then potentially if we have then a lot less tables than we thought we did. Because if I understand what you're saying correctly, is that we could have then like we might not need. Well, maybe we still do need 2 million tables. I think we don't like kind of just assume that number roughly without depending on the levels. I think it's the bug
Yeah.
with just this function, not anything else. We should
Yeah.
then document that.
Yeah.
Compute table. You like fix me or should I just do to do?
Yeah, just to do, and we can say like double check how this interacts with dynamic table sizes across levels. I think the way we were thinking of it is that we were saying, right, if our max table size is 64 megs, then we're going to work on an average of like 32 meg tables times 2 million or something like that.
Okay, yeah.
And so then this function is roughly still correct. But I think we could just
Yeah,
but
I mean this is just table yeah.
we can just work it out by hand down the line.
Yeah, I think we should just come back to this maybe because then we need to get back all the way into LSM tree stuff and stop thinking about the manifest. But I think I think what we got ended up with the maximum table count. I think we designed this data structure with the 2 million maximum table count in mind, I'm pretty
Yeah,
sure.
yeah,
And
yeah,
that means that this should work no matter how that calculation works out.
yeah. Cool. No, I'm
It's
happy, and
generic over
it's
the results. So yeah,
I'm with you. We do the anti-res technique, and we just put it to do there, and we keep going, keep moving.
cool.
And
Um,
just one question: the node size. Did we check what that was in the config? Did
no, I
we?
didn't.
Because we set
Um,
that, we worked that out in
it's
our
16
Excel.
kilobytes looks like.
Okay.
I'm pretty sure came from our spreadsheet. We tried a bunch of values, and this one seemed to work the best.
Okay.
Do you want to go back and look at the spreadsheet quick, or are you
Yeah,
cool with that?
yeah, well, you're on that side. I'll look it up on this side quick.
Cool.
Just so we can plug it in so we know we've got it. Uh, block block strategy versus table size. I'm getting there now. Let's check.
All right, I've got the spreadsheet.
Yeah, maybe it's better if we both there. It's actually, oh, LSM manifest. That's why it looks different.
You in
I
the
was,
wrong spreadsheet?
yeah, yeah.
I think
Happy
it's
New Year.
Discord.
Could you
Yeah,
sh could you share this one with me? I don't know if I've got it.
I think pretty sure I have. I can send you the link again.
Yeah. Oh, you have. Yeah. Okay. Cool. Perfect.
Get link, copy link.
No,
Here we are.
I can find it then. Yeah, great. Thanks. So we were actually looking at is it 64 kilobyte node size?
We had 16 kilobyte, I believe. So we were.
Yeah.
So we have in the code at least right now. Maybe we actually wanted to change that and just forgot to do so though.
Yeah.
Um, which looks to be the case, looking at these numbers here.
Yeah.
So maybe I'm not remembered to be honest. We'd have to go rewatch our old video to know exactly what we were thinking.
Yeah.
Um,
Cool. Let's add it to do also
cool.
in that config.
That's probably the most efficient way to do that. Actually, it's kind of cool. We have that option now.
Yeah.
Um,
Yeah. I
so
was
we'll
thinking
check
what we should do is at the end of each day, we could commit our work and then just capture that commit hash and put the commit hash with the video so we know like this was the start of the video, we're here, and this is where we
Okay.
get. Yeah.
Um, yeah. I wonder if we want. I think it's a good idea, for the record keeping kind of thing. I wonder if we might want to like put that work on a separate branch though, so we then can like squash the commits into semantic commits instead of just having like a single
Yeah.
blocky WIP commit every day.
Okay.
So we want to have like nice commit messages too and nice history.
Yeah. Maybe we should just do it whenever we do proper commits, then we'll just link the commits into the video.
Yeah.
Then
I guess the
it's,
dates will then line up with the video dates, so it'd probably work out anyways.
yeah.
Um, cool. We'll check this with our spreadsheet. That good for the to do, or do you want to add anything else there to remind us?
Yeah, we can just give the name of the spreadsheet so I don't
Our
go to the wrong.
LSM manifest
Yeah, nice.
spreadsheet. Cool.
Cool.
All right. Now we've got, I think we've got, so we just have the inputs kind of just these two constants, like the node size and then LSM table count max. And then from those two things, we derive our key nodes max and our table nodes max.
Yeah.
Um, Also from the size of the key and the size of the table info, but those are like kind of constant.
Yeah.
Um, cool. This all seems reasonable. And
Okay.
so, should we do the lookup path again, or do you want to say something else?
No, no, let's carry on. Thanks.
Cool. So remind me of what this is if I say something wrong, but I'm pretty sure. So this keynode count tells us how many elements in this array are valid, And then when we have a key, we first do a binary search in this keynode keymin array. This then finds us the keynode that might contain our key, and then we then get an index in this array out of that. So it's like then a keynode index. We take this and we go into this array and we go to that keynode. We do another binary search or binary search or itsing or whatever we want in here. We find the actual key inside this keynode. Well, we might not find the actual key yet, but we'll have then an even better idea of where it is inside the table node. And parallel to this, we have then also the we have then also the index from the keynode we found by searching here to the first table node that could overlap with that keynode. I think is how this goes. Yeah. And then we this is then a table node index, which will get us to the table node. And then we need to essentially search in the table nodes, just kind of in an increasing search until we like either find the key or go past it. That's my memory of this. I'm not remembering what the start indexes are for. I feel like this is an optimization, but I'm not sure for what anymore.
That one I'm happy with. That's where we find. So if I give it a try just to help me out, also the keynode keymin. So yeah, I'm with you. Keynode count is how many keynodes are active because we statically allocate that whole array. So yeah, like you say, which ones are valid. And then keynode keymin is kind of like our root node, where we just have the keynode. We have the keymin for all the keynodes that we have. Say we've got three nodes containing keys. So there's 3 keynodes. For each of those nodes, we'll get the min keymin. And then we'll end up with 3 keymins in keynode keymin, which is like our root node. So we're gonna binary search there, then we're gonna get to our keynode. And then that keynode is also got the the keymin table node is a pointer to where, or an index to the corresponding table node in our table nodes at the bottom. And the reason for that is to accelerate iteration. So once we've found where a key is, when we're iterating to actually get the table info, we don't have to start at the beginning always. We can speed up our search to start from where the keynode started.
I've remembered why we need these now too, I think.
Yeah.
Because these keynodes aren't full. It's an unrolled linked list, and so these nodes may be like only like half full potentially, or even less. And so keynode counts tells you how full each keynode is. And so when we go look at a keynode, it's only valid to look at the first keynode, to look at the first n keys in that keynode based on what the value is in this array, corresponding to the same key in keynode index. The start index tells us what index the first table node. This is kind of parallel to counts actually. This tells us like the absolute start index of each keynode, I believe.
Yeah. So that you don't have to iterate over counts.
Exactly.
It's a pre-computed like cumulative count at that index. So
that's why we have the comment that it's redundant, or the keynode count is redundant then.
Yeah.
We can get rid of this, but we have it for now just to keep the code simpler, and then we'll do the small thing to get rid of it once we're done with that. But we know we can get rid of it, so we're good there. Okay. And so now we end up with an absolute index. absolute key node or key index in the key node. How does that get us to a table node then?
The key node, that contains all the keys for which there are corresponding table infos, right?
No, I don't think so. It only contains. Oh, maybe it does. I'm not sure. I don't think it. I think you might be right. Yeah. I'm no longer sure though.
Yeah,
Do we have it
I,
in the spreadsheet? We probably do.
yeah,
I
I
think no, you're right. It does. We have it. It's in this calculation right here. For table count max, we do that many keys.
yeah,
So then it is a direct correspondence. So then we go straight from finding the index of the key in the key nodes is the same as finding the index as the table info in the table info nodes. It's just going to end up being a different node because these do fit less than per node.
yeah.
Um, cool. I think
So
we're up to speed now.
yeah, cool, cool. So we look in keynodes. We can get the logical index of the actual table info in table nodes, the logical index,
Exactly.
but that's going to be different to the physical index into table nodes.
Yeah. Well,
And
you'll end up being a different node in the unrolled list.
yeah, yeah.
A
So
different index in that node.
what we'll do is we'll jump to the earliest table node from keynode keyman table node. That'll get us to a slightly earlier table node, and then we'll just scan forward until we hit the logical index.
Yep. Using the start index to avoid
Yeah,
iterating all the nodes
yeah,
before that earliest node.
yeah.
Cool. I think I'm happy now. Are you happy?
I'm happy. Yeah. Do we want to comment this a bit more to help us ourselves out when it's Happy New Year next year?
Probably we should, yes.
Yeah,
I think we were going pretty fast when we wrote this because we didn't have much time left in that day.
yeah, yeah. No,
Okay.
it was cool.
So, um, um, this is the segmented array, I think we're calling it.
Yeah,
Array. Um, First key node count pointers are non-null. Null. The rest are null. Um, Nodes may not be full, or may, even if pointers non-null. Well, this null information isn't really semantically relevant. It's just a safety thing.
yeah.
Just so we get safety checks there, because only the first key node count pointers are. So maybe we shouldn't even mention this.
No, we. It's kind of more for keynote key min. That's where it's quite critical because we don't use null there. So keynote count is quite important for keynote key min, right?
Yeah, we're also not gonna. It's not like we're gonna iterate key node pointers to to see check if the pointers are non-null or not.
Yeah,
This is just known that they have to be non-null.
yeah,
This is just we only use opt here for get. We shouldn't even
no, it's cool.
see. Yeah, because the thing is, if we used non-optional pointers, we then have to set that to undefined, which
Yeah,
is then less clear if you'll get a safety panic
yeah,
because you reference it.
yeah,
It's actually better to set null here, I think.
yeah, yeah. And for keynote key min, that so keynote count is almost like keynote key min is almost like a slice, except it's an array, but the actual runtime length of it is stored in keynote count.
Yep. Um, is that good?
Yeah. Maybe we could do a comment also to say what it is.
Oh yeah,
This, uh,
that's probably more important. I
well,
should be doing dot comments as well here.
yeah, well,
Um,
both are equally important.
okay, so this is the minimum key of each key node
Yeah,
in the key node pointer um,
array,
segmented
array.
array.
Yeah. Should we add one more line above that and say this is essentially the root node. It contains the minimum key of each.
The root node
Yeah, cool.
in our tiered
Nice.
search or lookup.
Yeah,
Good.
yeah.
Cool. And then so start index definitely needs some more documentation too. Um, since a since segmented array is not since nodes in a segmented array are usually not full. Um, it is taking the absolute index of an element is O(n) over the number of nodes. I should wrap this though.
Maybe we should say physical index, so then we can contrast like physical versus logical, because
What do you mean by
otherwise,
physical here?
um,
I'm meaning logical with absolute.
yeah, yeah. It's fine. Just the opposite of absolute is like relative. Whereas if we say,
Well, I'm not sure what a physical index would be here even.
yeah,
Um,
I,
I think I'm thinking of relative as then an index within the node.
oh, okay. I'm actually thinking of it as, yeah, okay. No, cool. Let's do it that way then.
Well, I can also be a
Cool.
little bit more specific here and say the absolute index of an element in the array.
Yeah,
The full array is O(n) over the number of nodes.
yeah.
Um,
And maybe we should say, since computing the absolute index of a table node element of a corresponding table node element in the full array is O n over the number of table nodes.
well, really, it's the same thing there because it's an element. We're computing the same. It's the same index though. So what we really do is we compute the index of this key element in our key segmented array, which happens to be parallel to the table node segmented array in terms
Yeah,
of the absolute indexes.
yeah, yeah,
Right?
yeah.
I think this is. I think it's kind of. I think it's better to just like be unspecific about what element we're talking about here because it's true for both of them. Um,
Oh, okay. But if you find it in key min, then you're going to know straight away how to get to key node pointer. So there it's like one for one. So I thought this was only for how we jump from key. Once we get the logical index or the absolute index from key node, we then need to map that to the table node index. So that's what I
well,
thought.
it's the same index though because we have exactly one key in the key node for every table info in the table nodes.
Yeah,
So we've got two segmented arrays here. segmented array of keys and the segmented array of table infos, and they're parallel arrays.
Yeah.
There's a one-to-one correspondence between the elements in those two segmented arrays, and so
They just have different physical locations in memory.
yeah, we have them separated so you can do lookups faster, because when you're doing a lookup, you don't have to look at the table info, so you can just look at only the keys, and there's
Yeah.
fewer nodes in that array then, and looking them up is faster.
Yeah.
Um,
Okay. Cool. That idea for physical logical comes from like disk sectors and file systems, where your logical sector is like what we're thinking of as absolute index. So logical sector is where it is as the user sees the file system or the block device, and then the block device will physically map that logical sector to a different physical sector. So that's why for
right.
me it makes sense to have like they both have the same logical index, but the logical index for both is stored at different physical indexes.
Sure. I think logical
Yeah.
is fine. I'm not sure I don't think we should say physical though, because I don't think we need to. I think
Okay.
logical is a better. I think physical is still like a slightly confusing because we don't. It's not clear what exactly the index would be. Like an
Yeah,
index
because it
to an
isn't.
exact node, or I think
Yeah.
logical index of an element in the full array is good.
Okay.
Um, to avoid
I'm
this
happy with
cost.
absolute index. I just wanted to explain where I got that idea.
Yeah,
Like,
I see where you're coming from. I think
yeah,
logical is also better though, I think.
yeah.
I don't know. Absolutes, yeah, maybe absolute is better. I don't know. Alright.
Cool.
Things are always so wishy-washy. Um,
Let's go with that. I'm happy. That's great.
cool. Um, to avoid this cost, we the absolute index of the first element of each node up front. So we actually have to do this every time we modify the tree, right?
Yeah.
Um,
We can say we pre-compute.
you can just leave it at that.
Yeah.
We don't need the and store. This is redundant or
Yeah.
obvious. Each node. Just leave it at that, I guess.
Yeah.
Cool. I think I can copy the exact same comment down to here too. Um,
I think it's actually okay to not copy it because you can see it's dot index. It's the same
okay,
idea.
sure. And so this will be. So this one we don't even really need any comments because it's just the same thing as this, but simpler.
Yeah.
Um,
Yep.
well, we could say that this segmented array is parallel to this keynode segmented array.
Yeah.
This segmented array is parallel to the key node pointer array. That is the absolute indexes of key and table info and table are the same. Is that good?
And then maybe we should add one more and say, however, the actual node index and relative index into the nodes are different since the nodes have different
Yeah.
sizes.
Um,
Great. That's cool.
node X. All right.
Yeah.
Everything else seems to be spelled correctly.
Yeah.
Cool. Cool. That seems good to me.
Yeah, the only one we could do is just to explain keyman table node. And
Keyman table node. Oh yeah, I
and
haven't really done that yet.
maybe we could
Um,
actually move this comment we've just done, move it there, because it makes
hmm,
sense to explain why we do that. It's a way to
okay, yeah.
link the two together.
I think it's fine if they're not in order. I think keymin table node. Yeah, so this just it also just again save iteration and jump to the first possible table node that might match this key. And then we
Yeah,
iterate from there to the point where the absolute indexes match then, looking
yeah,
at the table node start index array.
yeah.
Cool. So what do I say
No,
there then?
okay, we could have just a comment and say um, this is a pointer to the corresponding table node for a given keynode's keyman.
Yeah, that's right. The index of the
Corresponding
key
table
of the
node.
table node containing the table info corresponding
Yeah, that's even better. Well,
to
oh, that's an interesting question. I wonder, is it not always the first key of a table node is the key min of a key node, or not?
no. The, this key this just contains the table info. If say um I'm not here's we could do a quick example, but this doesn't there doesn't need to be any one-to-one correspondence between these things.
Okay,
Um, between the node indexes, I mean.
okay,
I don't think. Or any like ratio.
okay.
That'd be the case perhaps if you end up with a case where the size of the key node, the number of keys in the key node is divisible exactly by the number of tables in the table node, perhaps. I'm not even sure if it's the case then, because then you solve the growth factor, where you split the table info
Yeah,
nodes sooner before you split the key nodes. 'Cause they're gonna end up growing faster probably. I
yeah.
think there's no strong correspondence here. So
And
this is correct though. This is the index of the table node containing table info corresponding to a given key node's minimum key.
yeah, nice.
This allows us to skip iteration.
To jump start, maybe, because
Um,
we still iterate, but we just jump start from where
jump
we.
to skip jump to or to jump over or just to skip table nodes which cannot contain the target table
Cool.
info when um, when converting when when searching for the table info with a matching, we want to say like it's the conversion from the absolute index into this array, but
Yeah,
then the table info into here.
yeah.
When given absolute index. Is that good?
Yeah, that's great. That's a good comment. I'm just wondering, like, as we, do you think? like if we look at this and see like what's in common between the two segmented arrays, it's it's like count pointer counts start index. I'm just wondering, like if we abstract this a little bit differently, it might make the thing easier to understand, or we could actually share a lot of code.
Um, well, counts we're gonna get rid of, I think, but maybe we could. Um, the problem is we also need then this thing here, but I think we should look at that more in terms of the code we have to write around this,
Yeah.
because maybe I'll simplify this code. Um,
Mm,
maybe it's not too bad right now. We'll have to look at this again for sure.
mm,
Um, where are we even at here? We've just kind of started our iterator. We've
mm.
got a binary search. Right, because we're just gonna use this. We just kind of grab this, I guess, for. Oh yeah, because the interface didn't really work out for this use case with our other binary search implementation.
Mm.
So we just kind of grabbed this one.
Yeah.
Um, so are we doing? I think we need to like use these things like in parallel though, because we always need to be like aware of the key node, so we can then like do this trick to then get to the table node.
Yeah.
I think they might be a little bit too coupled because I see what you mean. Like we have this key node count, um, and then it's like the like base segmented array thing might be able to be abstracted
Yeah.
using like these and
That's what
using
I
key node
was.
count, key node
That's
pointer, and start index thing.
exactly.
Um,
Yeah.
I'm not sure if that helped though or not. Um, we then abstract iterating to um, we don't actually do the same thing though there because like for the keynode one we jump straight to the keynode
Mm.
based on the binary search here, but for the table node we have to like look at this the result of this and then start iterating at that point to find the place. Um,
Yeah. Maybe um, if we could have like a segmented array type, and then we just have a few different methods that solve what we need to do with it.
yeah. Also might be useful for when we have to like add stuff to the array to handle the splitting code in one place. I think that might be
Exactly.
the bigger win.
Yeah.
Um,
Yeah. Because that'll be quite a lot of code, like keeping all this
cool.
working with it.
Yeah. So shall we try that then?
Yeah.
We need like a
And you're happy to try that now? Like you don't feel
yeah
you want to
yeah. I think that's
first
a good
code.
idea to try now.
You don't
I think we'll benefit a lot from abstraction there.
yeah, you don't want to first code and then dry it up. Like you actually think
Yeah, I think
we've
this is
ready.
good to do now. I
Yeah.
think we could already dry up this code a bit. Well, let's
Mm,
see. Let's look at this code we've already written and see if we can dry it up with this kind of thing.
yeah.
Um, so here, we first find the key node based on a binary search on our root node, essentially the key node key min array.
Yeah. Yeah.
Then um, this takes us to this is just the slice of key nodes here. What is this? Yeah, this is okay. Yeah, this is the slice of keys at the key node we find.
Yeah. Yeah.
Okay, and then we're going to binary search on this slice of keys in the key node, um, looking for key min again, and then we're going to add the result of that to the keynote start index, which will then give us the absolute index we're looking for.
Yeah.
Okay, that's all. That seems quite pretty simple so far. I don't think we could abstract that night. I don't think that would benefit from abstraction so far.
What
Um,
what what we could do here is the segmented array, it can have a method for given a node index, return the elements in that node. So it would
Okay,
basically
yeah,
do
we can make this
this.
nice here.
Yeah,
Yeah, cool. I'm with you there then.
yeah,
And then the start index has to happen separately anyways.
yeah. That,
Cool.
and then what we want to do here is index equals.
This will also happen separately as well because this is then the start, the key node, key min, table node. And
Yeah,
then here
that's,
we iterate until we find code's pretty tricky.
yeah,
Yeah. So this is we're just iterating until we find this table node which could contain this index.
yeah,
And then we want to return like it'd be tricky to find the array abstraction that could then give us this information, the table node and the relative index. Maybe the iteration happens inside the abstraction and we just kind of do that internally.
yeah.
'Cause-
I think the binary search shouldn't be an abstraction because the
right.
elements, I think you also are, like you would say the
Yeah.
same. So
I think
maybe
yeah.
we need like the abstraction has a concept of the node index and then with within a node, like the relative
Yeah.
index. There's
I
always
think
two
the
things.
abstraction needs to do the iteration here for us. Like
Mm,
it should handle these two things, like the current table node and the current relative index inside that node.
yeah,
And
yeah.
then the
So
other
that,
stuff, like the business logic around that
yeah,
will then handle these things in
yeah,
the level and
exactly. And
whatnot. And
if
so let's
you
look at
go,
the iteration. Yeah, but I'm convinced that this stuff should belong in the abstraction essentially.
that's actually
Binary
what I
search
wanted to say.
yeah,
Yeah, cool.
well, I'm with you. Cool. And then here, this is where we like didn't finish things, I think. This is
Yeah,
like the last thing we wrote before we went on break.
yeah.
Um, um,
It was pretty cool this session, like getting like fleshing this out so quickly, you know?
yeah, we dumped a lot of code pretty quickly, I think. Anyhow, yeah, and so now we're gonna like, hmm, we also need to iterate in both directions here. But this one only supports like one direction so far, I think. But we need to think about doing this for key max as well, perhaps.
Yeah,
Um, Anyhow, the abstraction should allow us to iterate in both directions along our segmented array for sure.
yeah.
Um,
We've got the same thing up there where given a node index, return the elements for that node. We do the
yeah,
same, those tables len
yeah,
and
exactly.
yeah,
And so this is just so I think what we need is an iterator that like holds these two things as state and just gives us the next element in this segmented array, which is a pointer
yeah,
to a table info.
yeah,
And then in here, we're going to do the business logic to see if we should actually expose that or not, or be done.
yeah,
Um,
cool.
yeah.
And
And so
the
we'll basically
iterator,
just yeah. This will happen in the abstraction. We'll get the table info out,
yeah,
and then we're going to do this logic here to do the compare keys to see if we've reached the end of our iteration, and if so, return null and like set the table iterator to null or something.
yeah,
Um, and then this will again happen in the abstraction, depending on
yeah,
which direction the iteration's happening. The
yeah,
iterator needs a direction, or the segmented array abstraction needs an iterator that supports forward and backwards iteration, I think is what we've realized.
yeah. And we're going to do that by passing the direction as data, like we do
Yep,
here. Yeah, good,
exactly.
good.
Cool. I'm with you now, I think.
Awesome,
Or I think
awesome.
we're both on the same page.
Yeah, I'm with
Um,
you. I'm with you now as well.
cool.
Nice.
So let's
It'll,
do some abstracting. Shall we do a
because
new file for this? I think we should.
yeah, because I was just thinking, I don't know how you felt when we were like re-looking at those fields, trying to understand it. The the physical layout, the physical, like the big ideas are quite simple. It's very simple. But
Yeah.
looking at that code, I was feeling like, wow, this is very tough for me. It's like very difficult,
Yeah.
or very
Just need
tricky. Yeah, yeah.
pub fn.
I was just
Uh,
thinking, man, this is like tough coding. Or
yeah, we'll get in there.
yeah,
It's not the base ideas are pretty simple actually. We just need to
yeah,
find the right way to write it so that it also reads simply.
yeah,
So we need here a max node count. And figure out the comp time um, max node count or node count max. That probably
yep.
our way of doing this node count max.
Uh, I've been
Uh,
I've been thinking we should put together like a document called Tiger Style MD, um,
yeah, we
and
probably should at some point.
put all of
Um,
these ideas, like these learnings, into it. What we've been finding
yeah,
here.
it should really be contributing to MD, I think.
Yeah,
But we
yeah.
should have a section in there called Tiger Style.
Tiger Style. Yeah, cool.
All right. Node count, keynotes. We need the nodes array as well. Um, and the node counts. So what the counts are going to be part of this. We'll just use the start indexes.
Yeah,
We can have counts for now though. We can get rid of it though.
yeah.
Um,
Basically, going to be three things: node count, node pointer, and start index.
Node count. And we also need the pointers. I'm just grabbing all this. We also then need the type of the array. So comp time t type. This will be this thing. And we also need the node capacity. Or comp time node t. All right. So here we've got. This is now just. Maybe this should be nodes.
Yeah, yep. I think it's going to clean up the naming of stuff as well, so we don't have
Oh
like
yeah, for sure.
keynote counts, keynote start index, all of that.
It's just separating our business logic from the fundamental data structure that's implementing it.
Yeah.
This is gonna make things a lot cleaner, I think. This will be node capacity.
This whole
Um,
idea of like abstract data types, I think if I
yeah.
understand correctly, comes straight from Barbara Liskov. Like this was her
Oh
idea, like
really?
to create
That's crazy.
abstractions to make programming simpler. Like it didn't exist before. Like
Wild.
yeah, yeah,
Yeah, I can't really think of programming without that, to be
yeah,
honest. Like,
yeah.
I've never programmed without abstract data types.
No,
Node counts. To get rid of this. Well, the nodes um, counts.
maybe we can even get rid of it right away, as we're doing this.
I think we should leave it for now because it'll make the initial code for this much simpler. And we
Okay,
can write tests, and then we can come back and get rid of it and update
okay,
without
okay,
touching the test.
okay,
That sound
cool.
good?
Yeah, yeah.
Um, cool.
And you know Clue from Tron, the movie? Uh,
Yeah.
Clue is,
KLU.
yeah, CLU was literally named after her Clue programming language. Like that's where Clue comes
Yeah.
from, like the name. You know?
He- It's been a while since I've seen that. Node count max. Okay, with the right names here, we've now got node. Um, it's gonna be like node data or node data node count. Hmm. I don't know. Maybe just node counts and start index is fine.
Yeah,
Maybe we'll find
yeah,
better names when we start writing code with it, but this seems all right for now.
yeah. We could just do nodes instead of node.
Sure. All right. And then these are all still statically allocated because these could get kind of large. I'm not sure what our node count will be, but I think it'll be pretty big sometimes.
Yeah.
Um, yeah. Anyhow, we need like an allocator to init then. So pub. I'm just gonna do the signature for now, probably.
Yeah. Shall we do this for 0.9, the allocate, and use the new allocator
Yeah,
interface?
sure.
Yeah.
Const mem is
I've
mem.
been I've been doing that on our next Zig branch that you set up.
Cool. How is that coming along? Is that like almost ready to merge, or?
Almost ready. I was kicking myself because you did like great work for IO to clean up all of that there, but
Yeah.
I suggested to Proti that we move some of the IO stuff out. So I've just got to
Oh, conflicts
fix
everywhere.
fix it up. Yeah, but it's fine. It's not difficult, but it's coming on pretty well. So just doing the allocate there, and
Cool.
I didn't get to it yesterday, but I'll just keep chipping away at it.
Cool. Yeah, let me know when you're ready for that to get looked at and merged. I can definitely give that a quick once over.
Yeah, I was wanting to ask you for a review. That'll be great. Uh,
Cool. Um,
but I'll bring in all the same style that you did for the blocks. You know, you introduced the block scopes again instead of the tricky one-liners in IO, where we were switching on the
did I?
results. Yeah,
That's good.
yeah,
Yeah, I think I made the code better there. It's
yeah,
been a while since we did that. That was like several months ago.
yeah,
Um,
yeah,
but yeah, cool. Um, there's one other thing. We probably should like go through our code and see if there's any places we can use the saturating arithmetic to clean up error handling or
yeah,
maybe avoid crashes. I think that could be quite useful sometimes.
yeah,
Um,
yeah.
like any,
I
uh,
want to use it in the set associative cache that we can use. And I think there might be one place where we could have used it, but otherwise, I don't think we use
yeah,
it.
we're not really parsing untrusted data, or we're not really using untrusted data very often, and so it becomes like less useful. It's very nice for untrusted user data, like or like when you're implementing a protocol that every number might actually be int max,
Yeah,
because it's legal to pass it in according to the protocol, it seems.
yeah,
And you've got to like handle that somehow without crashing.
yeah.
Um, we don't have that very often, it seems.
No, no. But it's a nice feature. Yeah,
For sure. All right. So init, we can just leave that for now. We'll return not void, but self. Okay. There's
cool.
init, and then we got pub fnd init. Those can just be to do. They're pretty simple. We need now to figure out what actual methods we need. We probably need, well, let's go back. We need the slice of elements for a node.
Yeah,
Um, that's pretty clear. We need to do this function, or this essentially.
yeah,
So node or elements,
and then
which will take
take
then
node
uh,
index.
what are we going to call this? We need a name for our segmented array variable. We just call it vary for both and use seg.
Yeah,
Just call it
that's
array,
fine.
do you think? Or should we
Ye-
just do,
Yeah, just array is cool. Or verbose, but both are nice. So the shorter one is fine.
we'll just do that, yeah.
Yeah,
And we also need a node, which will be a U32.
yeah,
We should make these U32s then, I guess, or node count should be a U32 instead.
yeah, yeah,
Node capacity probably could be as well, to be honest.
yeah. It should be. Otherwise, our indexing won't work, right? Or no? or it will?
Well, node capacity, yeah,
Yeah,
you're right. It
yeah,
has to be U32.
yeah.
Cool. Elements, now we're returning a slice of t, and I just copied this, but I forgot. Return. Not copy that? Okay, let's try again. There we go. Level keynote is not levels, it's an array dot nodes node
Nice.
0 count node.
Nice.
That's pretty clean.
Yeah.
Okay. Is
Yeah.
elements a good name for that? Do you like that?
I like it. Yeah. That's great.
Or should we call it node elements?
Yeah.
It's not all the elements in the whole array, it's just the elements for one node.
Yeah.
Okay, I think that's good. Um, so that's one helper. Should we like start like rewriting the code here to use the helpers already, or
Yeah. Let's do that.
this first? I guess we could. Let's try that. Why not? So here we can get rid of keynode count. Oh, I guess I'll do the second version of this below without the new version, which will be now keynodes.
I th I think we can
First
actually
key.
just keys and
Yeah.
tables.
We need key capacity and count max key um, key capacity key nodes max. All right. Right here. We get our nice highlighting.
Yeah. Nice.
Um, and we're still gonna need to have, you know, your key, what do we call it? Like key node key min. You still need this. Just copy this.
Yeah.
We still need this.
Cool.
And then we
Uh,
need tables,
yeah. Isaac,
which is
I'm wondering maybe I was thinking segmented array like the interface where we construct it, the comp time, the three args that we pass in. And I was thinking, what if someone swaps the two integers around and how could we like improve that? And then I was actually thinking, well, maybe the keynote capacity is kind of internal to the structure because the structure knows, the structure knows that nodes will be at
oh,
least half full.
you're right.
So
We can
maybe
just
we
divide
can
it.
improve the interface a little bit and pass in like
Uh,
node size and just a way that this
yeah.
divide by two is all like locked up
I think
tight.
node size can just be inside our segmented array.
Yeah,
Maybe. Um, this type is only going to be used here, and so we can just use LSM manifest node size here,
yeah,
and then just do the calculate the capacity here.
yeah. I
Well,
think we
node.
I think it's nice if we pass it in the constructor because you never know. Like, it doesn't really change anything if we just pass it in there.
Okay, so you
Does
just want to
it?
pass in node size here instead of capacity, essentially.
Yeah,
You can still swap the things there, right?
yeah. Node count max. I was wondering if we can't do it differently and maybe pass in node size and pass in capacity, or not capacity, but more like um, elements max, like which we get from table count max. And then that whole calculation we just pass in node size and table count max, and then everything works out inside. We
Okay, so like
basically,
all this stuff, you mean? Yeah.
yeah.
you're right, because this is like an implementation detail of a segmented array, this divide
Yeah,
by two thing. I
yeah,
see what you're going for, yeah. So our inputs here are node size and table count then,
yeah,
or just element count max.
yeah,
Okay, and then we need to copy this calculation essentially.
yeah,
I'll just stick that here. Um, so equals node size divided by size of not key but t instead, and then node count max that we want. I think it's just we're using node count max flow. I think that's good.
yeah.
X equals block or
And maybe we want to say node capacity also.
uh sure, yeah, we can do that.
Yeah,
Yeah, because that's what we call it below. It seems like the right way to think to call it. And then this here node fills up. It is divided into two new nodes. Therefore, oops, the worst possible space overhead is when all nodes are half full. All right.
nice.
And then we just need to update the names here. Node capacity divided by 2. For elements, min elements per node. And then we need element count max. And min keys per node is now min elements per node. Then we're good, I think.
Yeah.
Cool.
That plus one thing, I think the answer is in how we do the division on line 3, like node capacity divided by 2. What happens if there's flooring division? If
Yeah, I think you're right. If we use divcl, we wouldn't need to do that. Plus 1.
yeah, it's
I think
just
we also should wait until we do the code dividing the nodes to be sure.
yeah.
Um,
Okay. I was just
cool with that.
wondering, yeah, I'm cool. On line 3, if we could be more explicit, like the type of division we're thinking about, like
Yeah.
what uh, so
I'll do
we
a 2D. There's also the case where you have like the last node in the segmented array might only have one element in it. That's like the
yeah,
other edge case here.
yeah,
That's why I think we might need the plus 1 still. I'm
plus
not
one,
sure
yeah.
about that though. So,
I think that case was more static allocation because here, if the last element only has one node, if the last node only has one element, then we could actually have just inserted it into the tail node, which is half full, because it would still have space.
perhaps, yes.
So the one node with only one element, that was more static allocation where we're working out the cost, where each segmented array must have at least one node, even if it only has one element. It was that
Hmm.
coming, but I don't think it applies here. And I think
Well,
actually
do we like ever don't we like
from
remove stuff from the manifest sometimes though? In the case of a mutable.
yeah, we do, but I think if we when we remove stuff, we will try and compact also. Like if a node
Okay.
becomes less than half full, we'll try and copy it into the previous or neighboring nodes. Because that's what's quite nice to have the structure is now all of that code that's coming will also be here.
Indeed.
Uh,
Yeah. It's definitely a right way to abstraction is definitely the right call here.
yeah.
Um,
And then just one thing, min elements per node. Maybe we want the worst case. So we want a diff floor here to make it the
yeah.
smallest possible.
Yeah.
I think we could definitely already put that in, like use the
So the
built-in
div floor. Well,
to
it's
show.
already integer division is already flooring.
Yeah.
Um,
But just
so
to show that that's what we're thinking, like make it a bit clearer that it's
okay.
important to this.
You mean to use the div floor built in instead of doing this.
Yeah, yeah.
This is already div floor. There's no other way to do
I
unsigned division.
Yeah, I know, but I thought either we could just show it, or we can add a comment to say that we need to
Let's
do
add a
it.
comment.
Yeah, yeah, cool.
This, this
I,
is
d I didn't know
foreign.
that it's the same thing.
Yeah, yeah. I'm not trying to imply you didn't. I was just like, it's a bit
I d
ugly, isn't it? Like we don't
Yeah,
use
yeah,
the operator,
yeah,
foreign division.
cool.
Um,
But I mean, it doesn't matter if we don't know either. I don't mind that either. You're the language lawyer, the language expert. So I'm still learning, but
I
um,
mean, there's not a spec yet, so you can't really be a lawyer yet, but that will come.
yeah, yeah. There is a specs guy, but the
There's a
specs,
specs guy, and he's even more
yeah,
of a lawyer than I am.
yeah, yeah, yeah. But I think the comment is better because it actually like it's
Um, division. Just foreign division. That end of the comment wasn't good, I don't think.
um,
New capacity.
we basically want a pessimistic result. That's the key. Yeah,
Want
worst case.
to um, examine worst case
Yeah,
here.
nice.
Cool. Cool. I got just node capacity and node count max from node size and element count max. All right.
Yeah.
Now we can come back here and delete these things. And now, should I just delete this stuff too now? I don't want to get rid of all these comments yet. I might still
Mm.
want some of them.
Oh,
Array,
we can now pass in node size and table count max.
else in the table count max. I guess I can copy these.
Looks very nice.
It does. That's what we're down to now. It's just this.
Mm.
So I can probably get rid of this stuff already.
Yep.
Um, well, maybe let's keep this comment for now. I think we actually do need this comment still.
Yeah, we do.
And now we can maybe grab, well, do a comment here. That's kind of useless. The root node comment's still good. Maybe we should have the order here differently though, because the root node should come first, then the keys, then
Yeah,
that stuff.
I was just about to suggest that.
Cool.
And then we keep.
Anything else we're missing? I guess we can
Uh,
copy this comment into here. Oh nope, that's already there. Nice.
yeah,
Um, Ahead of myself, I guess. And we got nodes. We also still need node count. Um, that we need here. Then I think we can just delete these things.
yeah,
Cool.
nice.
All right, that got nice and simple.
Yeah. What do you think of the names Keynote, Keymin, and maybe those?
Oh yeah,
Yeah,
we probably need to fix those. Keynode, keymin, table node. It's kind of awkward.
yeah.
Okay. Um,
Here's an idea. So these correspond one to one with the actual keys, right?
yes.
The
Well,
only
not sure. Um, Also, we don't have this variable anymore, so we need to figure out a way to do that. Let me
Yeah,
do that first, real quick. We need to here expose, I think, node count max and node capacity.
yeah.
Maybe just node count max. Let's start with just that. So pub const node count max. Well, maybe we should just do it like this then. Just make a pub.
Yeah.
Okay.
Because I was
So we need to
wondering,
access that here.
yeah, maybe so what keynote, keymin there and table node, they are like it's the per node metadata. So you've got like each node has got elements, and then each node also has metadata.
Yep.
So maybe, I don't know, this is maybe complex. I'm just flying the idea by you, but maybe those two could also be in the segmented array. But for tables, it's like a void type.
Mm.
So it's a way that the segmented array can track metadata per node for you.
I think that's gonna get kind of awkward. I think it's
Yeah.
better to just keep it simple and do it like this.
Okay.
Um, if you're
Okay,
cool with
cool.
that.
Yeah, yeah, cool.
I think it'd be possible, but I think it wouldn't end up being cleaner. I think it just
No.
end up distracting from the code instead of like making things more readable.
Okay,
Um,
cool. Shall we drop keys down below keyman table node, or do you want to keep it in the order that we traverse
um,
it?
we could do that, yeah. I was just gonna do some like type stuff here as we then use that. Well, not that, I guess. We need to get the keynotes max variable out of this now, so we need like a cons keys array. So this, and we can do here then keys array dot node count max for there.
Hmm.
That makes sense?
Yeah, that's nice.
And this can just be keys array. And then this can go down here if you like.
Yeah.
We definitely need better names for these though. I think that's the main challenge now. Um, we could also just call this like root node.
Yeah.
Um,
Yeah, I think that's cool.
root.
Root.
Um, this one is then like key node or key node to table node. Key node to min. We could just call it like key node to min table node.
Is actually the it's this it also maps with the root. It's the because the root has all the key mins, and this is
Yeah.
the table node for those key mins.
Hmm. Indeed. So root.
Like root
So this
keys
is
and
like
root
root keys.
tables.
Yeah. And okay. I'm liking where this is going.
Yeah.
Yeah.
Uh, the only
Yeah.
difference is that maybe it's root table nodes because it's the
Yeah.
actual, but that's nice.
Yeah.
Cool.
I think that
And
that kind of solves it then, in my mind at least.
yeah, 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 that's very cool. What do you think of doing like we do elsewhere? Just when we type def, we can just say keys
Sure. Yeah. We don't need to put the
because
type in there. I agree. Just
we're
key.
close enough that you can see it is a segmented array.
Yeah, and it's better than just saying array because array is actually a little bit confusing there because it's not an array.
Yeah.
Um, cool. I'm getting happy with this. I
Yeah.
think we just need to fix up these comments now because these are now not totally right. Or they
Yeah.
use some stuff that's no longer here.
Yeah.
Um,
We could add a comment for keys just to clarify that this is, um, or we could, we yeah, like we had that question earlier, like does keys contain all the table keys, or is it a subset?
yeah. Um,
So I thought we
I don't
could
want to like
move,
type that just for symmetric for it to make it symmetrical. Um,
yeah, I was thinking that too.
just looks nicer if you have one of them typed up. You should do them both, I feel like.
Yeah,
Um, then we could put like these two next to each other, maybe. I'm not sure.
yeah,
This
I think so. And then
this
they
can still
share the comment.
this comment can stay. Yeah, yeah. I think we just do it like this. And make it like not a dot comment and
Mhm.
say just like these two segmented arrays are parallel.
Yeah,
These two segmented arrays are parallel. Um, Instances of key.
I would say maybe corresponding there instead of matching.
Corresponding.
Yeah, and then that's all
Cool.
great.
Now these need to be fixed up. Essentially, the root node are tiered. It's no longer essentially the root node. It is the root keys.
Yeah,
This is we can say this is the first thing we look at in our
yeah,
uh, place. Here, the first place searched. This is where the search starts, or this is the starting point. There we go. Of our tiered lookup approach. Minimum key of each key node in the just keys. That should come first, I think. Yeah, this is now no longer relevant. Cool. Oh, only the first key node count elements are valid. Oh yeah, that's right. So we still need to have yeah, only the first keys.node count elements are valid. Because now it needs to
yeah,
look at this field of our segmented array to know how many elements are valid here.
yeah,
I think it's all right.
yeah. I was wondering if we want to call it nodes len, like len. So it's as if we're simulating a slice, but maybe we don't want to.
I don't think we want to, no.
No,
'Cause it's not like it's not bounds checked, I guess.
no.
I think count is right.
Cool.
This.
Yeah. And that's what we do. We don't really use len, otherwise we spell things in
No,
full. Yeah.
it's not really a length. I guess length would be more if it was, I don't know, like a bunch of like nodes. I feel like you should count them, not like talk about
Yeah.
them like a buffer of memory. If it was
Yeah.
bytes, then we could use length. But it's
Yeah.
nodes. We should
For
count those instead. Yeah, I don't know.
yeah, here's like thinking of renaming things to duck type and any opaque. And here's another suggestion, like maybe zig slices, because they're slices of arbitrary types, shouldn't have length. It should be count. Like it's the number of
Hmm.
things in the slice, whether it's a U8 or a like a some value or whatever.
Yeah,
But
not
then it
sure.
because it's
I think often
always
makes more sense. Um,
sorry.
I think length often makes more sense though.
Yeah,
Um,
because
yeah, I'm not sure there's a clear win there.
it's just because a zig slice isn't actually len is not equal to byte size. It's equal to the count of elements.
Yeah, but it's also not called size. If it was called size, then it might make more sense to call it something different. But I think I think it's pretty much okay as it is right now. And length is a
Yeah,
little bit shorter, which is
it's
nice.
shorter. Yeah, otherwise it's going to be painful. Like, yeah,
Yeah,
no, perfect.
it's the index of the table node containing the table info corresponding to a given key node's minimum key. Is that all still good? Um, the index of the table node containing the table info corresponding to a given key node's minimum key. Yeah, that seems all to a given. Should we say a given root key instead?
Yeah,
Um,
yeah,
root to a given root key. And the rest of the comment seems good.
yeah.
Just wrap this a little bit more nicely.
Shall
All
we
right.
wrap? Shall we wrap that however comment as well? Just above keys.
Yeah, we can do that. Probably like automate this better. It's not very automated right now. I just need to find some good software that does comments properly.
Yeah,
Everything I've tried so far I've kind of hated.
yeah,
But Vim's got some really nice built-in wrapping stuff that works great, but it's implemented in Vim script, and so I can't use it here.
yeah.
Um,
It's comments are always a thing. I haven't got it in Sublime for some reason. I need to set it up properly for Zig
I
to
think
just
I've heard of some tools that will do it. There's one called like Par, but it's horribly complex.
Yeah.
It was like developed for like wrapping stuff in emails where you've got like multiple layers of like plain text emails where you've got like multiple layers of like indentation and references and comments and whatnot. And so it can handle like arbitrary prefixes and whatnot if you tell it the right options.
Yeah.
But it looks horrible. Like I have something. Let me just show you this real quick. It's just really funny. Um, or CAC RC par. Do I not have it here anymore? Oh no. Format. Oh yeah. This is yeah, so this is the attempt to use par, I think. Um
Yeah.
this is my attempt to implement this in Cocoon.
Okay.
Par didn't work out. Anyhow, par it just looks like a string of random numbers and letters and you can't understand anything. It
Yeah.
looks very similar to that.
But at least it's ASCII, right? Like not binary. It's ASCII
Yeah,
protocol.
it is. But yeah, it was like written in like the 70s or something.
Yeah.
And people still use it because it still works apparently, but
Yeah.
no one knows how it works. Anyhow, that's too much of a
Cool.
tangent. We need to get back to. I guess
Uh,
we got our stuff here now. We got these, so I guess we can just refactor this code now. So we just start with this and just refactor this to see how it looks now.
yeah.
Um, so binary search is now level dot root keys
Yes.
out of bounds. Yeah, we still need to think through out of bounds and negative lookups and whatnot.
Yeah.
Um, we haven't done that at all yet.
And maybe we want to pass a slice to binary search because we're,
Oh yeah, we definitely need to.
yeah.
We weren't doing that yet.
Mm.
So maybe we want like a level.rootKeys function.
Yeah.
Just put this at the bottom. I don't know. Like it's just a little helper.
Yeah.
Root keys going to be for manifest level, but no, it's just a self. This will return a slice of key. This will be return level.rootKeys 0 dot dot level.keys dot node count. And we can just use that up here. It's
Yeah.
how we've been doing this like other places. Just like do the balance checking only in one place when we've got this kind of out of bounds count for a slice. Okay, so now we've got balance checking on that. That's good.
Cool. That's very nice.
Now, yeah, we still need to
Is there shadowing there, Isaac? Like we've got level.root keys and the root keys
oh,
function.
there isn't actually right now. I think there probably should be, but
Yeah.
right now this compiler is fine.
Yeah.
Um, yeah, field and decal shadowing isn't a thing yet.
Yeah.
Yeah.
Maybe we can call the underlying thing like root keys array.
Yeah,
So it feels
that's probably better.
painful if we work with it direct and then we always work with the
Indeed, no
helper.
one will realize that.
Yeah.
Root keys array. Is that good? We'll have
Yeah.
the same thing for root table nodes, I guess.
Yeah.
Root table nodes array.
And root keys
That's
array.
better.
Yeah. Cool. Oh, and then table nodes, we just need to get the count from level tables.node count.
No, actually, it's still correct like this.
Oh, of course. Okay.
Still keys that node count max here,
Yeah.
and so yeah.
Cool.
Maybe this name isn't perfect, but or the root table nodes isn't the perfect name for this, but we can come back to that maybe.
Yeah.
Um, I don't know. I think we should want to see how it looks in the usage and see if it still makes sense to call it that or not. So right now we've got this will be happy with an empty slice, right? So if there's nothing in the
Yeah.
well, nope, it asserts keys that length is greater than 0. So an empty slice is not okay. So an iterate, you probably need to have like a null iterator we can return early if this is empty.
Yeah.
Um,
Shall we add a
so
comment?
I can just do like add an assertion that's not empty for now with a to do.
Okay.
If keys and then just say to do
Cool.
return empty iterate. That can just be our temporary thing. Then we need to also do balance checking here. But here, first of all, we well, we not need to check if key node is less than key node. Or maybe this should happen inside our segmented array. Config, yeah, so we haven't changed all that much. Cool. We can now here, node elements could return an optional slice perhaps to indicate that this node was out of bounds.
Yeah.
What do you think of that?
Why would we want to say that it's out of bounds?
Well, the binary search could like not find the node in root keys, right?
Okay. I was just wondering what we were addressing. Cool. Yeah.
But I'm not sure if this works the other direction with the key. I think we need a different binary search that does the opposite thing for key max, is what we realized last time, because otherwise this doesn't work
Yeah.
if we're
Yeah.
doing a key max direction of iteration.
Yeah.
I think we just need to come back to that though, because we still
Yeah.
got this assertion right here.
Yeah. So we just want a binary search that takes direction into account as well. And
I
does
think we
the
actually need two binary searches probably, because
yeah, we don't
well, I
want
don't
to.
know. It's maybe just the comparison that needs to be changed around. Yeah,
We
something
could
like that.
we could actually we can pass in the enum literal.
Yeah.
And
I
make
think we
it
don't want to branch on that every iteration of the loop there. We probably want to make it like comp time parameter
comp.
then.
That's what I was wondering. Yeah.
Yeah, something like that could work.
Because then
I
everything
feel like we
is
should be using our other binary search that's not. It's like there
yeah,
isn't the other one we have in binary search.sig, right?
yeah,
This one takes like API didn't work out there for some reason. Yeah, because you don't have values anymore.
yeah,
You just have keys.
yeah.
You just want to make it simpler then too, I think.
We could probably put these different variants all into the same namespace.
You probably should, yeah.
Yeah. Later. Yeah.
You want to just like leave that for as a to do? We should definitely
Yeah.
like add a to do here.
Yeah.
To do. Allow max key. All right. Getting a lot of to-dos piled up here, but I think that's okay. So
Yeah.
if this does not find the key, it will return one past the end of the array, I believe. Well, but let's go look at the test cases maybe to make sure that's the case. So I think these are the things we search for, and these are the results. Yeah.
Yeah.
And so if we search for 12, we get 6, which is 0, 1, 2, 3, 4. Yeah, so that's one past the end. Cool.
Yeah. It's the smallest thing that's greater than or equal to. The index
Yep.
of the smallest thing that's greater than or equal to. And if if the key we're searching for is bigger than the last thing, then we'll get the length of things.
Yeah. So we don't really need to return an optional there. We can just like check if key node is greater than keys.node count or level.keys. Then if it is, do this. And then here we just rely on the balance checking to
Yeah.
that's not what I want now. I want segmented array. Because here we'll get this is balance checked because we use slices in both
Yeah.
places.
I think that's better,
Or
Mike, because when we
yeah,
did the optional there, I was thinking it would be better if we don't have to do it, more
yeah,
explicit.
cool.
Yeah.
So now we just do here.
I think we've got a off by one though. On line 6, we need to actually say if it's greater than or equal to the node count. Because
Yep. You're right.
keynode's actually an index.
That's an exclusive count. You're right.
Yeah, cool.
Yep.
It's a new thing I've learned. Like the off by ones are either going to be in the conditions, they're either going to be like in the actual arithmetic, but they can just as well be on the greater than or less than. Yeah.
Okay, so what's going on here? Yeah, so here, I'm not sure what the right abstraction is at this point. What we're doing here is we're using binary search to give us the relative index inside the key node,
Yeah.
and then adding that to the start index of that key node.
Yeah.
So maybe we need like a relative to absolute index function on keys. That takes a node and a relative index and gives you the absolute index.
Yeah.
That sound good?
Yeah, that's cool. So
Cool.
it'll take the result from the binary search on the elements of that
Yep.
node and then give you the actual absolute. Yeah.
Self node U32. This will just really be, yeah, just adding the start index of the node. Return array dot start index node plus relative index. That's all that is really.
Yeah.
But I think extracting it like this might make the code here more readable. I'm not
Yeah.
sure.
Yeah.
Will now be const index equals level dot keys dot absolute index key
Key node.
node and then binary search results,
Yeah.
which could be out of bounds though. So we need to handle that. Well, can
Yeah.
it be out of bounds?
Um, it can't be because the key. Actually, no, it could be. It might be that the key actually isn't found. Mm, no.
I think what we do here though, it's not that the key. I think here we just kind of fall through though. I think we just accept that it's going to give us the next absolute index.
Yeah.
Yeah, I think here we're fine. Um, as long as the absolute index is still in bounds for the whole array. What will happen is we'll just start the iteration, but we'll immediately stop it because we'll be past the key max
Yeah.
potentially. We actually do we don't care if we find the exact key min. We want to always get like a range, right? We're
Yeah.
always looking for a range between key min and key max, and so we don't want to actually return a null iterator here if the key min's not found exactly. We want to then take the next the next key essentially in our array. And that's what this will give
Yeah.
us.
Yeah.
It'll give us one past the end of this key node, which is then the absolute index will be the first um, the first element in the next key node.
Yeah. Yeah. No, that's cool.
Cool. We need to comment that though for sure, because that's kind of tricky.
Yeah.
I think that is nicer. It's got like 2 characters shorter only, but
Yeah.
it's now here that we're doing an absolute index. Well, we could do here const relative index first, and then assign that to the binary search.
And do you not think we should do that explicitly here at the call site? I was wondering in absolute index if we should have an assertion that the relative index has to be within bounds for the key node.
Sorry.
I'm with you
Well, I'm
on
not sure
the
it does.
yeah,
You mean like the relative index has to be inside the bounds of the key nodes
yeah,
of
but
of keys?
um, or if we go look at the implementation for absolute index, but I'm with you on this idea that if the index is outside the key node, we bump the actual key node and go on to the next one
Well, we
internally.
don't actually have to do that though, because
Yeah,
this will still give us the right thing.
yeah,
It'll just give us here all we do is start index node plus the relative index, and so if this is actually out of bounds for this node,
okay,
then it'll give the index of the first element in the next node, right?
yeah, yeah. So that's fine.
We don't need to
Maybe
branch.
okay. I was wondering if we just want an assertion that I don't know if we want to assert inside here because this is in the hot path there. So, but
What did you want to
maybe we want some assertions for starters, and then we'll remove them once things are working. Just
Sure.
some training wheels. Like we could assert that the node index is within the count. Like for
Oh yeah, we definitely want to do that. Yeah.
yeah, maybe we can then add it to do here, like drop these asserts later. But it might help us just with testing things.
I don't think we need to drop the asserts. I think we should only drop them if we see some profiling to say we should drop them.
Yeah,
Um,
yeah. Okay. I think these are in the data plane though, like for doing lookups. So it'll be pretty hot.
yeah.
So that's why I would say
Yeah. Well,
we once we've
and
tested
a
it,
better
we
way to do that might be to actually just turn on release fast mode for these functions.
okay,
And
cool. Yeah.
then we'll
That's
get benefit from the assertions because then we'll tell the optimizer, oh, you can assume this.
yeah, yeah. Cool. Cool. That's it. Um, then relative index also, well, we know what the result is, so we could check that the result is also in bounds of what the total structure contains.
Um, the result is in bounds. Well, is it going to be? I think it might be one past the end. If you look at the last node and if we're looking at the last node right now, we don't find the binary search in the last node, we'll end up with relative index one past the end of the entire arrays of the maximum, or we'll end up with an absolute index past the end of the absolute
Yeah,
of the whole array, I guess.
yeah.
And then we'll handle that here, I think.
Okay.
Um,
Okay, cool.
Not sure how we handle that yet. Maybe we just kind of keep on going with that, and then our iterator returns null right away. We're now going to use this to construct a table, an iterator essentially. Um, that's the kind of next step is to figure out how to abstract this bit into an iterator.
Yeah.
Um, so I think the right thing to do is just make this iterator return null right away if you give it like an index past the end.
Yeah.
Um,
Yeah. Okay, cool. And we kind of have to do it at the call site here because we don't know what the absolute index is until until we've actually asked the segmented array what it is. So
Yeah.
the segmented array can't then panic at that point because it
Right.
doesn't then give us a chance to, yeah.
Yeah. So I think we can get a comment here. We could if we like said the relative index has to stay in bounds for keys, then we could panic if the
Yeah.
absolute index was out of bounds here. But I think it's better to do it this way actually.
Okay.
Because it becomes less branchy.
Yeah.
Um,
Cool.
yeah, leave the comment
That's
here.
that was
This
the
might be out of bounds.
question that I was wondering is how soon do we want to fail? Like how quickly do we want to panic? And but I
Yeah,
think
so maybe we should do that. Maybe it is safer to first here check if the relative index is out of bounds and then do the same thing here and
yeah,
then do the assertions in here. That's like
yeah,
less could go wrong that way. So let's do that for now. We can
okay,
then come back and refactor it if we find it's faster to do it a different way.
yeah,
So assert is less than, well, we can just say, you can here get, no, I think that's the right way to do it. Assert that the relative index is less than, um, well, we don't have counts anymore, so we're gonna get rid of counts, but we can come back to that for soon, I guess.
yeah.
I mean, actually get rid of counts. And this should be less than or equal to, I believe. No, just less than.
Yeah.
Yeah.
So we're saying that the node must be in bounds and the relative index has to be within that node.
Yep.
Yeah. Okay, cool. And
And
then
then here
we could
we
add
can
it.
then,
We could add
sorry?
it. Sorry, Isaac. We could add it to do there, like um, just at the top, so like enable release fast for this once tested, or um,
Or consider.
yeah,
We don't want to do it just blindly.
no,
Uh, Here we now
um,
need to just check if this is out of bounds.
yeah.
Equal to keys.length.
It might actually be that we only call these when we construct the iterator, in which
Yeah,
case it's pretty cheap. Although I don't know if we're using the iterator when we just do point lookups, because if that's the case, then it's back to being expensive again. So
yeah. I think we do need to do this when we'll need to do the same thing when we do point lookups, I'm pretty sure.
yeah,
Um,
okay,
so
okay,
it probably will be expensive, yeah.
cool.
Um, an iteration is just a point lookup plus then iteration after the lookup. It's the same code
Yeah,
for the initial point lookup. That's
yeah,
what we're doing right now, kind of.
yeah.
Uh, well, all right, and then here we've got next. So now we need to, I guess, think about the next steps here. So now we need to figure out how we want our iterator to work.
Yeah. Shall we take a 5 minute break?
Sure, that sounds
Uh,
good.
what do you think? And then we can carry on a bit more till lunch.
Cool.
Okay, awesome. Catch you
Back 5 minutes.
5 minutes. Yeah. Yeah, Isaac.
Hey, Aaron, ready to get going
Cool.
again?
Yeah, great. I just
Cool.
finished some dried banana and like peanuts and raisins stack.
Nice. All right. Yeah, so I guess we just need to figure out, well, there's two steps here. We need like one, on one hand, you have an iterator, so we can iterate over elements in our segmented array. And the other hand, we need to like do this logic to get to the jump to the right place in the segmented array based on it's now our root. We now have this root table nodes thing,
Yeah,
and so this is returning the wrong type. It needs to be fixed. U32.
cool. Good
Um,
catch.
Soon return the index of the table node we just start iterating at, I guess. So maybe we need like a go to index function. I'm not sure. What would that
Yeah,
return then? Or I guess the iterator just needs to like initialize with the start index. I think that's what it is. The
yeah,
iterator will take to start the iteration, to initialize the iterator, will take in um, an absolute index, which is the start index, um, and then like a start table node to start looking for that start index, perhaps. That'd then be the result of this root table nodes um,
yeah.
thing. Yeah, I think that's what it is. And then that'll give us
Okay.
just an iterator which then stores a node and a relative index
Yeah.
to be able to, yeah. Hmm. There's probably a trick we could do there with like modular arithmetic to store these both in one integer, but we can talk about that later. Um, if the node count is small enough.
Yeah.
Um, but maybe that's probably a bad idea. Um,
It's a cool idea.
it's probably not a good one though. I think it just introduce too much
Yeah.
complexity.
Yeah.
But I think it would be possible.
Yeah.
Um, so yeah, let's just write the iterator then, I guess.
Yep.
Um, uh, equals struct. Well, do we need a forwards and backwards version? I'm not sure. We could store direct. Well, here we're storing direction at runtime. In fact, I wonder if it would be better to have like two separate iterators, make it generic over the direction, and do the branching there at comp time. Then you only branch once at the start of the iteration to determine the direction, and there's no more branches.
Okay.
So maybe the branch
Yeah.
predictor like makes that not very relevant. 'Cause if we'll always take the ascending branch for a given iteration, and always the descending branch for the other iteration.
Yeah. Maybe that's quite important. I hadn't thought of that. I like that it keeps our code less branchy, but actually deciding on the iterator. But then again, if we do that, it means we're changing iterator types, which makes it more complex, where we store iterators like in our compaction and things like that.
Yeah, well, we just store it would be still a pretty concrete type. It would just be instead of we store just iterator, we store like iterator dot ascending. I think
Yeah.
that'd be all right.
Okay.
Um, Making it generic over only the direction, it wouldn't be too bad. Um, I think that'll work.
Yeah.
That would work out.
Okay,
And
cool.
here we just take up the direction. We take it the direction at comp time instead of at runtime. And then we just need one branch when we call this function um, to determine whether to be create comp time ascending or comp time descending iterator. I'm not sure if that's actually performance win or not because I'm not sure if the branch predictor is like good enough to see that this variable's descending and always take the
Yeah.
descending branches. Probably, yeah, it's probably like the first iteration will be
Maybe
slower or something like that. I'm not sure.
maybe I think it's a good idea. Like, what do you think of like a hybrid where the constructor takes direction as runtime because we only know it at runtime, um, and then the iterator returned by the constructor, that is then comp time.
That wouldn't really work though, because you wouldn't know which type to return at compile time.
Exactly,
That would be
yeah.
then like a comp time known. The type has got to be comp time known, and that's dependent on what direction gets passed here. It means the
Yeah,
direction also must be comp time known.
yeah,
Um, Otherwise, you'd be, yeah, I don't know. That doesn't, that's, I think that's fine, but make the direction comp time known then, though. That would just look like we'd have a switch that just has two branches, or ascending or descending, and
yeah,
calls the iterate function with a different comp time known value, based on that runtime value.
yeah. I was wondering if that isn't then maybe punting the problem and kind of showing us that it is a runtime thing, because somewhere we
No,
have to just,
that's fine.
yeah,
Well, yeah, you're right. We would essentially have two branches of whatever code uses this.
yeah.
Um, So where are we going to need the ascending iteration or descending iteration? I mean, using key max instead of key min.
Yeah, it's basically going to be when we do queries, so the API, the user is going to decide whether they want ascending or descending order coming in when they query Tiger Beetle.
Okay. Then we just kind of yeah. I think
I
we
like,
should just keep it runtime for now until we have a
yeah,
strong reason to not do that. Um,
exactly. Yeah, because I agree. I think it like keeps the code a bit simpler. It's nicer just to pass in a direction and everything just works. And there's no
yeah.
switching of the types or branchiness at the call site. Keeps it simpler. And then yeah, then we just see.
Okay, and then we need here also we need the node and the node index and then the relative index, I guess.
Yeah.
Yeah. I'm calling that relative index is good because that's what we call it like up here too.
Mm,
Um, Direction stuff here should come first. That's pretty important.
yeah.
Okay, and then in the constructor, we're going to take in, well, first the array. Array needs to be mutable? I don't know. I don't think it does need to be mutable. We shouldn't need to modify self through this, should we?
No.
I wonder why it's mutable here. I don't think it needs to be. I think we should make this unmutable. It should probably be, it should be a constant pointer actually is what it should be.
Yeah.
So we don't want to copy it here. And same thing here. Okay.
Uh, just oh hey hey Laris.
Sweet.
I was wondering, Isaac, the const self pointer.
Yes.
Just this always confuses me because we've chatted about this like many times. uh,
Yeah.
so what how is it different here? Like that we're not just letting the
Um,
compiler figure out to
yeah.
pass,
So
you know.
it's because we're not just passing it, we're storing it in a struct, this iterator struct. So I didn't want to copy all the
Uh,
memory of self into this array
okay, okay,
field struct. So
okay,
instead we just store it to
perfect,
the pointer.
perfect. Yeah, now I understand. Thanks. Yeah,
Same thing with like the standard library hash map, I believe.
yeah,
Other iterator
yeah,
makes.
yeah.
Um, so
Cool.
here, I think here we want to take in like an absolute index. So or start index or
Yeah.
start absolute index. I'm not sure. Absolute start index. Don't know different ways to say that. I
Yeah.
think that's the cleanest way to say it, maybe. It's kind of
Yeah.
verbose though. And then
We've actually got two
start.
indexes that we pass in, right?
Yeah, we're passing also the node.
Yeah. Don't we even pass an absolute index or not?
We pass in this. We pass in the This is the absolute index we're passing in.
Sorry. Okay. Yeah.
And this start node isn't really necessary. It could be passed in as 0 and we'd still do the right thing. I'm not sure how to
Yeah.
convey that yet. I just need to return an iterator. Let's document these arguments, I guess. This. Well, it's not even. If it's already set to 0. I'll just leave it at that, I think.
Yeah.
We also need the direction.
That's it. Shall
Okay.
we put in our other iterators, do we put direction up front or do we put it at the
I
end?
don't remember.
Okay, it seems at the end there. That makes
Yeah.
sense. Okay, cool.
Seems fine.
Yeah.
So now we can basically copy this code. Well, let's see what the calling code is going to do now. We're going to basically do for just const iterator equals level dot tables dot iterator, passing in index and this. Well, it's not gonna be that exactly anymore. It's gonna be level root table nodes key node. Yeah, that seems right. Cool.
Cool.
And then the direction as well. I think that's it. So, yeah. And all this stuff and we'll get out of this, we'll just get an iterator we can call here. Maybe we just do that in line, I'm not sure. You don't need this relative index or table node stuff anymore.
Yeah.
This can just kind of get taken, put here, and we'll figure out what to do that in a second. Maybe this should just go in like inline here.
Yeah. That's cool.
No need for that. Okay. Cool. Root table nodes. Maybe we should put this in a variable, then we can like make this line, make this a one-liner instead of wrapping it.
Yeah. Nice.
Better.
Yep. Start node.
Oh, should we call this like root start nodes? or that's not really better. I'm still not totally happy with this name,
Yeah.
but I think it works out okay. You'd probably come up with something better there, but maybe it's not that
Yeah.
important.
Yeah, I'm thinking also, I agree with you. I feel the same. I don't know how you feel about this. I feel like it's pretty tough, or is it just because it's a new year?
This code in general,
Yeah.
I think it's all right. It's not trivial. It's definitely not trivial code, but it could be worse, I feel like.
Yeah. Yeah. I once had to do some Reed Solomon coding, like a Reed Solomon codec, and do the
Okay.
encoding, decoding, and then I had to make it faster and use Cauchy matrices, or like to
Ooh,
do like
yeah, I've heard of those.
Galois fields and stuff. And I just said to myself, don't worry, one day you'll look back and you'll understand it. And I was, but I don't know, this feels harder. Like this feels much worse.
Really?
Much more scary. Yeah.
It is a
Because,
little bit scary, but I don't know.
yeah,
It'll become a little bit trickier when we do both directions here. Um,
yeah,
yeah, I think this
that's
will be all
the,
right, though. We just gotta
yeah,
test it.
yeah,
It's a lot
yeah,
of place for like off by ones, though. You're right.
yeah. I think it's the direction stuff that when you add, because that's a whole nother dimension. Like now you've got to
Yeah,
work it one way, work the other way. So, but it's cool. We'll get there, like you say.
for sure. All right. Just now,
And I
this
think
balance
I
check
think
here.
we're like we are solving it the right way. We're abstracting it nicely. Um, the that's good how we're doing it, you know. And it's just maybe it's just
Cool.
these names here, like coming back to where we started off.
Yeah, as I forgot some parentheses there. This
Yeah,
this one could definitely be improved. I don't have any ideas right now. I think about us to move on and finish up.
yeah,
Um, so let's first do the initialization here. So this is our start node. So just say var node equals start node, and then while node plus one is less than um, array.node count. So we had, didn't we? Yeah, that's the same thing. This is now we're
yeah,
kind of looking ahead. So while this node is not the last node in the array, and what's the other part of this? Table node start index. This is the this is just our calling it just start index, I think. Yeah.
yeah. Start index, and then table node becomes just node.
Yep.
Yeah,
It's now index becomes absolute start index. Okay, so there's now we're not always looking at the next node, not the start node. So we're
yeah,
saying if the next node is is less than if it's inside the array. So if the next
yeah.
node is not out of bounds,
Yep.
and if the start index of the next node is less than our absolute start index. So if our absolute start index is after the start index of the next node, then we're gonna
Yeah.
go to then we're set our node to the next node.
Yeah.
So I feel like we should flip this around to make this track go the other way. What do you feel? What do you think about that? It reads more nicely. We do like absolute start index
Yeah.
is greater than or equal
Cool.
to this. That's kind of what we care about
Yeah.
more.
Cool. And
And then,
then on line 4, we have it, we can just rename table node to node.
yep. And index is now absolute start index minus level dot or not level, but array.
Yeah.
We've got the node and the relative index and the direction and everything else we need, I think.
Yeah.
Or the other direction, we'll have to go the other direction here. We should probably do that now, shouldn't we?
Yeah. And before we get there, just to give ourselves some like safety rope, shall we
Yeah.
just add assertions here everywhere? Like on maybe that's the key. It'll give us like some reassurance. Like all our functions, we just assert preconditions, postconditions.
Yeah.
Later on, we will you know if it's data plane, we'll do release fast, but otherwise release safe.
Yeah,
But
for sure.
so here we could actually like check our preconditions absolute start index. Is that within bounds? We can check start node. And then after we've
To check that that's in
yeah,
bounds, I think we actually want to allow it to be out of bounds. This is the one tricky case where
yeah,
we actually just want to return. We can actually just avoid more branching there by checking this is in bounds is actually a little bit tricky. We just want to
yeah.
allow it to be out of bounds, then we'll return null from an iterator in the first time you try and iterate.
Okay.
Pretty confident about that one. This is the simpler check. The other check you can need to do is then say like array start index. Well, you need first of all you need a separate check for hmm,
What about if we go on to start node, we can assert that start node is less than array.node count.
sure, yeah, for sure.
So that we would have already had an early return and not even arrive here if the segment array is empty.
That's
Uh,
good. For the
and
start index though, I think we do want to just return like an iterator that will return null right away. I'm right at
okay,
the last bit of the function real quick. Just,
okay,
return
cool.
calls array, and then we're gonna have what else? Just need direction, node, and relative index. Maybe I'll put that in line, but I think it's fine like this, perhaps.
Yeah,
I kind of want it like that, actually.
that's nice. Yeah,
Cool. And then here, so the absolute start index, we're we don't even care about that here, actually. What's gonna happen is we'll end up with, if this is out of bounds of the array, what's gonna happen is we'll get to the last node in the array,
yeah,
because this will be true, and this will also be true, and we'll increment this, and then that'll give us then to the last node in the array, and
yeah,
then we'll increment this again. Well, this will be false then, because then we'll be past the end
yeah,
of the array if we increment it again. We'll end up with the last node here, and then we'll take the start index of the last node and subtract that from the absolute start index. So we'll have a relative index outside of bounds of the last node, and then this all works out nicely, I think. Well, maybe we should handle this especially here.
yeah.
I think we should handle especially so we can then insert in the iterator the relative index inside the bounds of the node always.
I was going to say
Um,
that too, that we do that same assert we did elsewhere. That
yeah,
then and I also thought after the while loop we could assert that node is less than array.node count.
sure.
I know it's pretty obvious from the loop, but the loop is so tricky that it's just good to like
Yep. And then here we're going to also then we want to just like check absolute start index. Well, we want to make sure relative index is in bounds for the node.
Yeah.
And to do that, we can say, well, we can check. Actually, what we can do is check like why we exited the loop. We checked it because we ran out of nodes. Um,
Yeah.
so we can say basically like if node plus 1 is less than array node count, and so if node plus 1 if node equals array, if this is the last node in the array,
Yeah.
and this condition is still true, the absolute start index is greater than, well, maybe it's better to just check if the relative index is in bounds for this node here. I think that's simpler.
Yeah.
Um,
Yeah. We can actually just call our absolute index function, passing the node and the relative index, and
oh,
that'll
we
check it for
could
us.
absolute index function.
Well, actually, those are just the two asserts we need to copy.
Relative index is less than array.counts node, yeah.
Yeah.
We already have node less than array.count.
Yeah. Yeah.
Well, it's array.node count. I messed that up here. It should be array.node count.
Okay, cool. Nice. Good catch.
And then relative index is less than, I should have just copied it when I was up there. Array.counts node. Well, it's not an assertion though, it's just an if it's greater than or equal to this, then we need to return. Then we're going to say we want our iterator to return null right away. To do that, we want our node to be out of bounds. We want to like make it our node out of bounds, so then the iterator returns null, right? And the iterator on the next function, we're going to check if the node's out of bounds is the first thing, and then return null in that case. So here we
Yeah.
can just say node. Well, does that mean we actually want to flip this check around then to just have the loop do this part for us? We could just let the loop iterate until the nodes, but then we wouldn't be able to get this thing, so we wouldn't be able to
Yeah.
index here.
Yeah.
This seems like the right way to do it. Node out of bounds.
It
We should put
seemed
a bit more context. The target, well, on a higher level, do we expect this to ever happen? Yeah, we do. Okay.
I th I don't know how you feel about this one. I'm not so sure. I think maybe we need to like step back and see how we use the iterator and just make it that we don't have all these special checks, that it just works and simpler, like less code.
Yeah, we
I'm
could leave this check off too and just not do the assertions. Then it would still work.
Yeah,
So we do that.
because
You just wouldn't be
because
able to
what
do.
I was I thought here maybe if we can assert, then we should. But otherwise, if we can't, then
Okay.
you see here where we do node plus equals one, it seems that we also have to then update the relative index, having done
You
that.
wouldn't need to though, but it kind of depend on how we do next function. I
Yeah,
think
yeah,
I'm thinking you're right, and we should just kind of make the code as simple as possible, and then maybe have a few less assertions because of that. But
Yeah,
favor code simplicity over assertion count. I think
yeah.
that's probably a good way to go. Um,
Okay, just so it all just flows through the iterators, everything. Yeah.
Turns a T, I believe. Actually,
Yep.
it just return a star T. I think it does return
Yeah.
a star T.
Yeah.
Pointer to table info. Yeah. So we won't actually use this iterator for keys. We'll only use it for the table info.
Yeah.
Um,
And
Maybe this
Isaac,
isn't in the right
just
direction, but yeah, sorry, go ahead.
yeah, to just understand a bit better, the star T is important because it's only really like function arguments where you don't do a constant pointer. You let the compiler decide how it's going to pass the argument. But for
Yeah,
return
well,
types
it'll
and struct
actually, I
fields,
think we'll try, or yeah, I'm not sure how good it is yet, really, in practice, but it'll try to do
yeah,
no copy on returns as well,
yeah,
because it can basically treat them as an out pointer argument, or an
yeah,
out argument. The compiler is
yeah,
able to do that transformation in theory. I'm not
okay,
sure how good it is in practice yet, but I think just
yeah,
returning a pointer is what we want here anyways.
yeah. I like that. It's kind of how we think about it. Yeah.
Yeah.
And we're going to return a const pointer probably because we won't mutate the table
Yeah, probably.
info. Yeah.
Well, yeah, I think we probably should return a const pointer here too then.
Yeah.
Right?
Yep.
Cool.
The
All
nice thing
right.
with the segmented array abstraction now is that we can test it like um,
Indeed. Yeah, that's definitely
much
good.
better. Yeah.
We
Cool.
can test the other one too, I think. We
Yeah.
just need to like plug in different
Yeah.
constants. We definitely want to test it. Um,
Yeah.
all right.
It's pretty cool now. Like the actual design we've got for the manifest is we've got a root node, and then we've now got two segmented arrays. We're using like instead of just like a B plus tree with segmented array at the bottom, now we've got a segmented array like for the next for the index nodes as well. Um,
Yeah, we got a three tiers pretty well laid out now. It's very clear how they kind of
yeah,
work now too
yeah,
in these four fields.
yeah,
All right, so the first thing to do here is check if node's out of bounds. So we can copy this from our current code, I think. Um,
yeah.
let's try and handle ascending and descending right away too, I think. Um,
It's
and
a
instead of
good
doing
time
this
to
assert
do
round
that.
switch, I think it's not very hard in this context to do that properly.
Yeah.
Um,
And I think too, like once we start doing it properly, like direction everywhere, we'll also feel that our code is solid. Like we've actually, we're starting to do everything and
yeah. Direction direction equals no, it's no longer what we want to do. Ascending equals. So we're going to do this. This needs to be a comma. Okay, so if the node is out of bounds, we're going to return null. How do we handle that? I think we actually do want to. Hmm. So here, I think actually it's cleaner to actually do this little thing I was talking about here. I think might want to flip around this code though. Um, what we want to do is like allow this thing to iterate past the end, or give us an invalid node. Not sure what we want to do here. Here we just want to
the
check if it's ascending. Let's write this
uh,
check immediately first, but we were saying if it.node is greater than this is not the right thing anymore. It's now it's dot array dot node count.
Yeah.
Node's out of bounds, then return null. That's kind
Yeah.
of our exit condition. And then other direction is then if node is, well,
Yeah.
here we then get into the problem with 0 and wrapping.
Yeah.
If
I've
we
got
make
another
node,
idea. I don't know if it's a good idea though, but
right?
we could add a field to our iterator like a count, like, and we do a countdown because that way it works for both directions. It's simple. It's wasteful though, and now we've got to do extra arithmetic. But
Obviously,
we
yes.
just
I'm not really convinced. I guess you'd then need like a start though. Still need to know like the direction you're going, and then so you just kind of
it's just a
know.
counter of remaining elements in the iterator.
But
So
how do you know which
it's
element you're at? Like a start. So you
um,
have like a start element, and then remaining for element count.
when you basically when we construct the iterator, we work out how many indices are remaining according to the direction, and then when we're using it, we just count down. But I don't think it's a great idea. I'm just
Yeah, I'm saying we would also need then either still need some absolute node index to know where to count from or where to count to.
yeah,
Like if you have a just count, you don't know where in the array you're iterating.
yeah,
And so you'd have to like count from something or count to something. And so like it wouldn't help too much. I think the most reasonable
yeah,
way to do that would be to, yeah, I think that just complicates things, to be honest. So
yeah,
I've not, though it would actually help with this 0 issue where we have now, um, like if node if node is 0, which is valid, and we try and subtract again, we're going to get, yeah, overflow.
yeah.
Maybe we should just have a done bool. That's probably the
I,
simplest way
I
to do
was
this.
I was almost going to suggest, in the back of my mind, I was thinking E or F, like have a Boolean, like when you get
Yeah.
there. Because
Then
that way
this,
we push the logic into the constructor, and
yeah, I
maybe that's the
think
whole,
that's just super simpler. It's not much
yeah,
overhead at all.
no.
Um, okay. I think that should go
And
last.
I think there's one principle here too, is that I think where we were running into trouble here is that we're trying to use the node and relative index, we're trying to use them for more than one purpose. So we're using it to
Yeah.
track, and we're trying to use it to know when we're done. And in like cryptography, there's like a principle that if you ever have a secret key, you should only ever use it for one purpose. So like if you set up a TLS handshake to set up your
Yep.
symmetric keys for AES counter or GCM or whatever, then you don't do the like you say you've got Bob and Alice and yeah, Bob and Alice.
Yep.
What you could do is you could have just one shared key to do symmetric encryption both directions. But what TLS actually does is it takes the shared like session key, and then from that it cryptographically derives a key for Bob to use and a key for Alice to use, so that they're now using different keys. But they know what the other's key is because they also know the shared key. And then when Alice does encryption, she actually takes her key and still derives yet another special purpose key just for encryption. And when Alice does authentication, like for Max, it's the same thing. So you
Yep.
never ever a key is never used for more than one purpose. Like so Alice has her own key just for encryption, she has her own key just for authentication. But it's just like a good principle, like keep the if you've got like a cloth for the coffee machine steamer wand, only use the cloth for that. Don't use it to wipe the kitchen counter as well. Like it must be separate, you know. Uh,
All right. Yeah.
but I don't know, like long story. But I think maybe that's the key. Like that's what we realized here. We need a separate Boolean because
Yeah.
we're trying to
You could do
use
it
we're
the
trying
other
to use
way,
it.
but I think it's going to simplify the code to do it this way. And it will
Exactly,
make,
yeah.
in this case here, it's now clear we can just set done if relative index is out of bounds, right?
Yeah.
Um,
Yes.
and so
Yeah.
we're going to say if relative index is greater than or equal to array dot count is counts node we could say so actually we should do that here, I guess. Dot done equals this condition.
Yeah. There were some things in our consensus protocol as well, where I ran into some trouble where I was trying to reuse something for more than one purpose. And each
Yep.
time whenever I like you split, I can't remember what it was, but I think it helps a lot, like to
Cool.
simplify.
That's
This
the right check too. I got the up comparator right.
yeah,
Yeah,
yep. I think this is really nice, like this idea of
it's much better. Yeah.
putting it in line.
And then that's just the first thing we check, and so we know that we'll do the same thing for the other iterator too, I think. And they'll
Yeah,
simplify, they'll allow us to solve all these assert to-dos. Turn an empty iterator. It's now very clear how to make an empty iterator. You just set done to true, and nothing else
yeah,
matters. Um,
yeah, exactly.
I like that.
Whereas, whereas before, like we had a whole lot of different ways to indicate done, and we had to get
And
them
it also
all
depends on
correct.
whether you're ascending or descending. It would depend on the iterator direction how you indicate done. And that
Yeah,
seems bad.
yeah, and we had to get every single one of them correct, otherwise it blows up. Like,
Yep. That's much
yeah,
more foolproof. So we
yeah,
this is the best thing. We don't trust ourselves. We gotta check ourselves with our code.
yeah. Hey,
Default model.
nice t-shirt by the way. You wearing zinc today? Yeah,
Yep.
cool, cool. Did
Get
your
the
did your
tiger.
one of did your Tiger Tracks
Yeah.
one arrive as well?
I haven't gotten a t-shirt yet. I've only got the hat so
Okay,
far.
okay,
We'll
cool.
see. Hopefully I
It
can
should be
get it sometime soon.
on its way. Yeah,
Cool.
nice. I'll wear zinc tomorrow. Yeah,
Awesome. All right, so now we got our done variable. We got all these other stuff is now irrelevant if this becomes true. But yeah,
yeah,
and I think it's a fine way to just do that in line. I think it's clear enough what we mean. It's kind of, yeah, it's pretty obvious, I think. Anyhow,
yeah,
here we can now, we just need to do this logic here now. Where is that? We need to first then just get our table info pointer, or our t pointer, red equals, now we're going into the data. We need to actually just first do like its elements, it dot array dot node elements, it dot node, and then we're going to index this with it dot relative index, and then take the pointer to that.
yeah,
That's our return value. That's pretty simple. And we're going to do this logic essentially. And now it's here where we need to swap an ascending for the first time.
yeah,
So it dot index plus equals 1. Nah, actually, I think it's now, I think we just want to switch an ascending right away. Switch it dot direction. And then do all this in here.
cool.
Just to make it easier for me to think about for now at least. So now we're going to do
Yeah,
it dot relative. Index plus equals 1. Yep, it. Oh, you know what? I think this might be wrong.
yeah. It
Because what if this node's not at the end?
exactly. Yeah,
Well, then
yeah,
this wouldn't have returned true though. This is still right. So, but if this is the case, then we can assert that node equals, um, is the last node in the array. So I think we should take this out and do that assert.
Yeah.
So here you can have like const done equals, just put this in a block, and then the L break false. Here we're gonna true, and we're also gonna do an assert node equals, or node plus 1 count.
Okay, nice.
And that's a pretty important assert to have. Otherwise, we can we can skip over data.
Yeah. Can we flesh out the else clauses here as well and see what we can assert?
You like do it like this?
Yeah.
And then here, we can here assert that there's nothing we can assert on node here, other than that it's in bounds, which we already have.
That's part of the if. Yeah.
I don't think there is anything else we can assert there. The relative index has got to be in bounds, but that's also part of the if. If you just hear the minus assert the relative index is less than the array that counts node.
Yeah.
You like. Other than that, I don't really see.
But that is the actual branch anyway. So.
Yeah. So I think we'll just. I think we should just. Oops, not quite all that, but I think we just do that.
Yeah, that's cool. Okay, nice. And then done. So if it's true like that,
Is there a better way to do this without like the true and false things here?
No, I think that's nice like that. I'm just trying to understand it like the relative index. We take the absolute start index minus the start index of the node.
Yep.
And because we found the node we wanted, now we're somewhere in there.
Yeah, so we've actually kind of overloaded the term start index here.
I was thinking that too.
Call this, we should just call this absolute index, I think, and the document to be the start.
Yeah.
Start. And, or just call it, say, absolute index at which. This is too awkward. To start. Is that good?
Yeah.
Then we don't have
iteration. Yeah, it's better. Yeah. I was thinking exactly the same, that we're overloading. And it's nice to have relative and absolute lineup like that.
Definitely. And it's very clear that how you get to relative by doing absolute minus the first index in the node.
Yeah.
We can also call this like first index instead of start index.
Yeah. Or we could call it absolute index of the node.
We could do that too, yeah.
Which, because it shows that it's the same kind of unit.
Yeah.
As
I'll try it out.
Because that way for relative index 0,
now we're stacking though.
Okay.
I feel like start index is okay. You like first slightly better? We can just we can definitely should document that it's an absolute index.
Yeah.
Or we already have documented that it's absolute index.
Yeah. Well, is the shadowing coming through in our function helper?
it was if I rename this to absolute index, then we shadow this, or this function's got the
Yeah.
same name as the field.
Yeah. We could also just call that one index because it's already clear that we pass in the relative index. I don't know.
Hmm.
Maybe not.
I think it's more clear if we have it explicitly say absolute index, but
Yeah.
I think start index is also not that bad. I think better, slightly better might be first index
Okay.
or first absolute index. I think first index might sound better though. So
Uh,
actually how we describe it in the doc comment, I just realized. Absolute index
it-
of the first element of each node. We
yeah.
use the word first here. So I think first index is good.
Yeah. If we wanted to, we could even say absolute index first element uh, for a
You're
node.
breaking up a bit there. Could you repeat
Oh,
that?
okay. Okay, cool. We could even just go Tiger style and say absolute index of first element.
Just like nice
Then
and
it's,
long and explicit. Um,
yeah, because then it's crystal clear, like what it, and that's kind of what we've done in the comment.
yeah,
Absolute index of first element.
yeah,
I think DHH would be really proud of us now.
yeah. So now we've got all the lines are still under 100 somehow. So
Yeah.
I'm happy with that. Yeah, it's very explicit. Like you
Yeah.
can't mess that up. What it means now.
No,
I like it.
yeah.
This is now
Ru-
super
Ru-
clear.
yeah. I once learned Ruby and it taught me something like this is how we can just do these long names.
I've never done really much Ruby. I've written probably less than 100 lines of Ruby in my life.
Okay, then we've done like the same amount probably. Yeah, it's close. Yeah. But this
Definitely
is
never really
nice now. Like, yeah, you have like I'm really happy with this naming now.
happy with it. Yeah.
Mm.
I'm still not totally happy with how this done thing is written, but I'm not seeing a better way to do it.
Yeah,
I figure it's not super clean to use the block here. We could like use a variable, like a var done equals false, and then if in this if set to true, but I kind of like having it in const because then it's like this one
yeah,
can't mute
yeah,
it, but
yeah,
it's more
yeah.
resistant to
I
future changes
agree.
to this code.
Yeah, const is better. What we could do if expression, and then we can do the assert. So assert not done or node plus one equals array dot node count.
Oh,
After
I like that.
that way, yeah,
Try that, yeah. Um, First, just say like if done,
yeah,
assert that,
yeah,
then done just equal this directly. You don't
yeah,
even need the if
yeah,
expression.
yeah.
This is much cleaner. I'm happy now.
Okay. Do we not? Oh, and you say we don't need a. Okay, cool. Maybe shall we add a new line there? Yeah.
Cool. That's much better.
Sweet. Very cool. Uh,
Cool. I'm happy with
nice.
that. Back to here, I guess.
Yep.
So if we were ascending, then we increment the relative index, and we're going to check if the index is in bounds for this is greater than or equal to it dot array dot no or counts it dot node. Actually, we could use here maybe a temporary variable for elements or node elements.
Yeah.
This. And you can just node elements dot length there. Still under, that's good. Or instead of iterator that counts and like duplicating that code, we just use node elements.length.
Yeah.
And it's clear that we're working on the same slice as we are there. And then this version's useless now. If we've now gone past the end of a node element, we reset it.relative index to 0 and increment the node. And then we need to check, we need to set done though, if node, node is greater than or equal to, we can just say equals and then assert that's not greater than. Equals it dot node count or it dot array. What we called it? Yep, cool.
Yeah.
Then we're gonna say it dot done equals true.
Yeah.
And here we're gonna assert that node plus then
In a else branch.
you can do it here and also I'm not sure. I was gonna do it like this.
Cool.
Not sure if it's better or not, but it just seemed like the way to do it right now. I'm not sure why.
Yeah.
Then you have it kind of like lines up more. Do you show that you're covering
Nice. We could do the same for relative index as well compared to node elements length.
Sorry, what?
Oh, we could have the same assert for relative index. We could just check if it's equal to node elements length.
Yeah, you're right. Okay.
Yeah, do the same pattern.
Your video just dropped out for me for a split second. I'm not sure if it's on my end or your end. It seems we
Yeah,
have a
I don't
good
know.
Discord, but it could
When
also be
our
on my end usually.
course, it could be. I'm at the office, which is pretty good. When we started our call, then the video wasn't great quality. It could be Discord probably, but your video is also dropping. I don't know how is mine dropping quite a bit.
Hmm. It's just like I'm losing a few frames every now and then, but
Yeah,
the audio seems to be all right mostly. So we'll just keep going and see if it gets bad to the point we need to do something.
take a lunch break.
Yeah,
Yeah,
that's what's coming up soon.
yep.
Node elements dot length. All right. Yeah. Cool. And yeah, that's perfect. It's now nice and symmetrical.
Yeah, yeah.
Done equals true, and now
Do we have
that's
to,
now yeah.
and when it's true, we don't have to bump any indexes because we've solved that problem. Uh, that
Yep.
we just literally set the boolean to true. That's it.
Yep.
Yeah.
And if it's not, if we're not done, then we should do with asserts that the indexes are in balance here. I think.
Yeah.
I think we shouldn't do them first because I think we want to keep this thing that if we're done, we don't look at anything else, and so we don't really have to care about trying to get the indexes right if we're done.
Yeah.
But right after if we're not done, we need to make sure the indexes are in bounds.
Yeah. Cool.
I think it would at least be a good idea to check them here.
Yeah.
We can always remove the asserts if there's too many asserts.
Yeah. Do you see that done is actually an anagram for node? So where we've got on line 14, if it node equals array node count, and then it done, and you've got this
Indeed.
perfect, plus it lines up,
I don't know if that's good or bad. It seems like it'd be easier to like misread one as the other now, or
Yeah.
mistype one as the other.
Yeah.
You could use finished instead, but I'm not sure.
No, I think it's cool because you've got the type safe different types and stuff.
That's true, yeah. So Zig would help us there. It's not like C.
Yeah. Yeah, I'm really happy
It,
now. I'm feeling like this feels really solid. Like we've solved these problems nicely.
cool. Yeah, I've messed this up, haven't I? I'm shadowing a function name with this variable. I'll just call this elements instead of node elements.
Yeah,
Um,
cool. And I wanted to suggest maybe we can rename ret and have like in full just say element and return the element.
yeah. Okay. I was going to do an assert here, but I'm not sure what it was. I think it's the same thing I was going to assert here, which maybe isn't the point. Um,
Yeah,
I think that's redundant if I assert there. I don't need to.
yeah,
Um, there's asserts in here already, and we've got asserts now here and here as well. All it's
yeah,
left to do is do the descending branch, which is going to be the reverse of this essentially.
yeah,
And we're going to now then return element at the end.
yeah. Awesome. Very, very cool.
Okay, the descending branch, now we're going to say, we're going to set minus equals 1 relative index. We're going to assert relative index is greater than or equal to 0.
Yeah.
Well, that seems like kind of
Which
redundant now,
we don't need
but
to do that because Zig will do that for us. Yeah.
yeah. Then we're going to say if it's equal to 0, relative index equals elements. Well, I think we should do the node first, and then set this to like
Yeah.
node count, or array counts node. Does that seem good?
Yeah. And then it needs to be counts
Just
minus
has to be
one.
ordered as there.
Yeah. It needs to be array counts node minus one.
Are you sure?
Yeah, because the relative index is zero based indexing, whereas counts is the
Yeah.
quantity. So we have to
Right.
convert it
I
into
see.
an index.
I understood node minus one, like inside, subtracting one from the
Oh,
node
yeah,
instead
yeah.
of from the,
Yeah.
which wouldn't make sense. But this is you're totally right there. Cool.
Cool. It's amazing how well like you understand me that I can even like communicate to you and you just realize like what I mean or like because I think if I was driving and you were telling me stuff I would be like
Yeah.
"Oh, like what must we move?" Yeah.
Sorry, you broke up there again. So I didn't
Okay.
understand you that well.
Uh, yeah. No problem. No, this is good. Yeah.
You're saying cool stuff about how well I understand you, though.
Yeah, yeah. Like with driving, I think if
Uh,
I was driving, and I think we've had it before where I've been driving and then you've told me like suggestion, and then I can't compute where I must move the cursor or where we're at, yeah. But you just got the yeah,
well, thank you.
yeah,
I do think we've got a pretty good rhythm together now.
yeah,
Um,
yeah. It's working really nicely. Like I'm glad we pair programming because I think this is exactly the type of work where it makes sense. It's
yeah,
just
for
so
sure.
critical. Yeah,
It's a lot of like code. We got to just keep so much stuff in your head because it's such a big system. You're writing
yeah.
two heads to keep stuff in. It's a lot better than one.
Yeah, yeah, just definitely. And then at the end of the process, you actually end up with two heads who understand the code instead of one.
Yep,
So that's
indeed.
worth it. Yeah. And then it also means you
It.node is less
can
than or equal to
like
it.array node count. This needs to be flipped around.
it also means you can start to grow that understanding through the team because now two of us understand it, then one of us can do
Yeah.
reviews for someone else, or it trickles down. Yeah.
So I think we actually need to put this inside. There's something tricky here because now we want to check if it's 0 again, um, right? Because that would be then if it's 0.
Yeah.
And we also need to subtract 1 here. Actually, if we're getting to the end, we need to do this before. We need to do this before we subtract, and then actually like
Yeah.
break from this.
Yeah. Good catch.
Otherwise, we'll overflow. We can do the same
Yeah.
control flow here up though if we want, just make it symmetrical. But now it's not
We
very
should.
symmetrical anymore.
Yeah.
This is right now though, I think. Um, yeah.
Yeah, that's cool. So if relative index, I think we've got a bug. No, okay, we don't. So if the relative index is 0, we want to then decrement node if it's not already 0. And there we go. And then relative index to the new node -1. And we always want to decrease relative index. What if
Yeah.
relative index is 0 currently? How do we handle that?
It's like so if relative index,
Is already
so
0.
yes, we've definitely decrement relative index to 0. I guess we still want to do a loop there.
But you know what I mean? Like what if when we've captured the element,
Oh, so really we want to decrement this like after we've checked.
yeah.
Yeah. So I think what the fix is actually this. We want to move this relative index minus equals 1 to after this.
Yeah. And
And
put
then
it in
do
an
just an
else.
else here.
Yeah.
Yeah. Yeah. Because we don't want to do it twice in this case, and we don't want to do it at all if it's equal to 0.
Yeah.
Okay. Now it's also symmetrical here again. So now I've got check against 0, else decrement. Check against 0, else decrement.
Yeah.
And then, yeah.
Cool. Does the same logic make sense upstairs for ascending?
I'm not sure it does, but let's try it. Yeah. So I think it doesn't. This is now like very different. Let's try and do it like the same way. So if it should make sense actually, because it'll be actually easier because we don't have the here we can also just stop right exactly at the end. So we say if it
Yeah.
dot relative index equals elements dot length minus 1. Then we're going to say if it dot node equals it array dot node count minus 1. These minus ones make me think it's not really the cleanest way to write this though. But it would
Yeah.
be symmetrical, which would be good,
Yeah.
perhaps. Uh, um, Here we're going to do then node equals 1, and then it. So that's the same logic. It does work out. Yeah.
Yeah. It's actually nice. It looks a little bit strange, but it kind of shows you what we're really trying to do. Like if we're at the last element, if we're at the last.
Yeah. It's not the normal way I'd write code, because normally I'd write it like you'd use like so it's one past it's this like
Yeah.
size, and then use less than instead. This actually works out fine for an iterator like this.
Yeah.
I also like a lot that's symmetrical because it makes it a lot easier to make sure these two things stay in sync and they both work. If you
Yeah.
find a bug
Because
in one, there's almost certainly a bug in the other one, the same bug in the other
ex
one.
exactly. Yeah. Yeah. Shall we copy that assert, those two asserts that we've got into the else branches?
Yeah, we should. And so I think we can keep the same assert here. Hmm, Your
We could
video is
actually
just
just.
flashing on and off.
Okay.
Oh,
Sorry.
you're back again.
Cool.
No worries. I don't think it's their fault.
Uh, yeah. We could just copy that into the else branch and make it a less than clause. Or we can do it up top. That's fine. Because
Is that
now we do
correct
have
here?
we
I don't think it's just a less than now.
yeah,
Yeah.
yeah, less than. Okay, cool. That's actually great like that. And then that's even better.
And then here it's the same thing, just a less than. And then here we don't bother with the asserts because of their unsigned integers, and we get the asserts that they overflow.
Yeah,
Okay, so that seems good to me.
cool. And then that we can drop as well. That line there. Is it can we not actually hoist that it node assertion compared to node count and actually just hoist it right up and keep the two asserts together? Because they should always be true. It doesn't
Oh
depend
yeah,
on
we can put them
the,
both at the top.
yeah,
Yeah,
that's it.
we can even put these outside the switch, couldn't we? Um,
Yeah, because it should always be true regardless of direction. And
just
then,
put it there. Yeah,
yeah.
cool.
And within node elements, do we have some assertions there within our
We
helper
do.
function?
Um, assert that the node is in bounds essentially.
Okay,
So
cool.
we are actually already doing well. No, we
We
don't
just
actually have
have
any
to,
assertions here. That was the absolute. We should probably add more
yeah,
maybe, but this is we don't. That's the
yeah,
only thing we could assert there. Yeah,
cool.
I guess we
Yeah,
could.
we that's cool. We also need to unwrap when we go into the nodes optional um, because it's the it's that array is containing optional pointers there within node
Oh,
elements.
you're right. Yeah, we just always just do that
Yeah,
question mark. Cool. Seems good to me. I like how symmetrical this is. It's really nice and clean.
yeah, yeah. It's very cool.
Cool. So that's this iterator done, I think.
Yeah,
Um,
that's awesome.
cool. Well, it's the initialization. I think this is all done too. I mean, we have all the code we need here. And this should then
Yeah,
iterates in the direction we want until it's done. All the direction codes in one switch, which is much nicer than what we had before.
yeah,
Yeah, this is coming together.
yeah. And then from here, all we'll need is like our constructor logic for the segmented array when we want to do inserts um, to rebuild.
Oh yeah, right. We haven't even gotten to that part yet.
Yeah,
We've just been thinking about the read path first. I think it's
yeah,
usually the right thing to do first when you're like figuring out a new like data structure or format or whatnot. Figure out how the
yeah,
data's got to be on disk so you can read it or in memory, and then you can figure out how to efficiently write it and make sure that it's well, yeah.
yeah, yeah.
I think the
Cool.
next thing to do is do the next iterator layer above this, like the one here in
Yeah,
manifest level.
that's cool. And see that it actually makes sense what we've done. Like we can use it. Um, how do you think? Shall we stop for lunch, Isaac? Do you like a half-hour lunch? Hey, Isaac, are you there?
Hey, am I back?
Hey, Isaac, you're back. Cool. Shall we
Maybe it'll
break for
work better
lunch?
now. Yeah, I think
Yeah,
it's a good time to break for lunch. Um,
awesome.
see you
Okay,
back, or when you want to come back.
shall we do like a half-hour lunch till quarter past, and then
Quarter
I
past. Um, sorry, half hour
uh
lunch to quarter past. Sure, we can do that.
yeah, and then on the other side after lunch, then I'll have like 40 minutes or so before I've got to head off. So then we can do like a
All right,
just a
cool.
final
Good.
final bit.
See you back
Uh,
after a quick lunch then.
yeah, yeah, nice work. Cool. That you just now.
Cheers.
Hey Isaac, we back.
Yeah. We back live?
Back, yeah, we're back live. Yeah,
Share my screen.
cool. There we go.
Cool.
I I took a walk on the roof of the office here on the side of the building. You can like walk
Yeah.
around it all the way to
Nice.
the back because the cricket stadium is right next door, and there's a test match on at the moment. I think it's with India. I haven't actually checked.
Neat.
So yeah, but I couldn't hear the crowds or anything. But you can basically walk almost right up to the stadium. So
Wild.
yeah, and pretty
Cool.
sweet weather this side.
Yeah, it looks beautiful out there. Wish we had some better weather here, but we'll get there. It's
Yeah,
January.
yeah. Are you
Um, so yeah, we get the
cool?
iterator cracking. Um, I think we've got the initialization pretty much finished now. Should we check this like one more time?
Yeah,
Um, our segmented array iterator is expected to start node is less than the array node count, but I don't think it has any other requirements.
yeah,
Absolute index, we handle the absolute index being out of bounds here. Because we set the done right there. So that's fine if the absolute index is out of bounds.
yeah.
Uh,
I had an
we
idea
should
there.
document that. Suppose.
Yeah,
Or- Go
yeah.
ahead.
I thought we could check the absolute. We could check the start node. That the this we could check the start node relative to the absolute index.
Oh, yeah. That's a good idea. Um, yeah. So we're basically just checking like the other way around of this.
Yeah,
Um, less than or equal to absolute index.
I think it depends on the
Equal is possible.
direction as well.
Oh, this doesn't actually handle direction at all yet, this function. So we should do that
Yeah.
first, I think.
Okay, cool.
You're right, it does depend on the direction.
So
Neither of those does this function, though. Maybe we should do it for here first to figure out the direction here.
yeah,
We also might want like an empty iterator.
yeah. I think
We can leave it
let's
now.
maybe
But
let's
yeah.
stay in segmented array first and finish up that constructor. Is it that
Yeah.
where we were, and then we can jump up
It's
to
not
manifest level.
not totally clear like how start node works for descending direction.
Yeah,
That's what I was looking up here again. The start node we get from this root table nodes
yeah,
array. The start node is based on the min key.
yeah,
So we have to basically just go like, maybe we have to just increment this by 1, or we maybe have to increment the index into root table nodes by 1 for doing the other way around. Something like that.
yeah. The it's so we expect that, so like if the direction is ascending, then we expect that the start node it'll have a min key that is before or equal to the key we're looking at, or another way, like it'll have the absolute index of that start node should be before or equal to if we're ascending.
Yep.
That's with min keys. But the start
Yeah.
node is always min keys. We don't have a key max.
No. So you can get a key max kind of like going the other direction. So say that's why I want to look at this first to see like what these things
Okay.
even mean for
Cool. Cool.
descending, so we can know how to implement this properly.
Yeah.
I think what we need to do here is this check can stay the same. This search needs to now be different. We're searching for now the key max. Should we just like implement this part first then? You think?
Okay.
I think this part doesn't really depend on what we do here. Now this is like actually this is like a smaller piece of this function where we just need to pass in a node to it to do this stuff. Tricky part.
Yeah, at segmented array, where we do the iterator, passing in start node, what would we expect here? Like ascending is okay. If we descending, then we iterating this way.
Yeah.
So we
just want
decreasing.
something. We essentially just want the opposite of this condition.
Yeah.
We want absolute index of first element of the start node to be greater than, well, actually it's not the first index, it's the last index though. Or
yeah.
I don't know what it is.
Yeah, we have to get the start node, and then
it's the last index is what it is. Yeah.
Yeah, and work out the last index using the first index plus the count for that node.
Yeah, so I feel like we should have like a helper for.
Yeah.
Oh, maybe we should have a helper for this that does bounds checks.
Yeah, that's a good idea.
Then,
because at the moment we don't actually. Yeah, at the moment we don't actually do any bounds checking there, right?
Well, we do for the with node count max, but not based on the node count itself.
Yeah.
So we definitely need to improve our bounds checking there.
Yeah.
Maybe we should change the name again then to. Not sure.
I think that name is okay. We just need to, because we
like first element, last element then.
Exactly.
Yeah.
Yeah. Because we only gonna store the key min.
Yeah. Let me just put these down at the bottom maybe. Like we shouldn't have. I don't know.
I do think
fine up here, but
yeah,
like the internal helpers can just go down here at the bottom, I think.
Yeah.
Cool. First element.
I do. If I can say so myself, I think that absolute index of first element, that name, it's got to be the best name we've come up with all year.
Maybe it's a hard competition though.
Yeah, it is.
We've got some other ones we aren't thinking of right now.
Yeah.
Okay, so first element, we'll give you then turn array. Well, insert node is less than array.node count. And then return array.absolute index of first element node.
Yeah.
And then for the last element, it's a bit trickier. Element. Well, we can do the same assert. That's still valid. Now we need to do node plus 1 though, and if node plus 1 is out of bounds, then we need to like just add. Actually, we can do this.
I think it isn't. It isn't that actually. I think it's.
Yeah, I think it's something else too.
Yeah,
you just add the count of this.
The count to the index -1.
And no branches. Yeah. Count node. No counts, I think. Yeah. Cool. That's nice.
And cool. Do we need? Is there off by 1? We are in terms of indexes. So say the absolute index is 0. There's 3 in the node. So we do need to still do a -1, I believe.
Hold on. Yeah, I think you're right. Well,
if let's say that
if this is 0.
Yeah.
Looking at the first node, for example, if this is 0.
Yeah.
Then this this is exactly the index. Yeah, you're right. -1. Yep. Things are sneaky.
Yeah. But then I'm wondering if, what if the node is empty? But that can never be the case. A node can never be empty.
No.
Okay.
So we're kind of asserting that the node is not empty here, which I think is a fine thing to do.
Yeah.
Yeah.
Cool. Maybe we should do what do you think, Isaac, like the helper names, like index of first element, index of last element. So that it's clear that it's returning the index.
Yeah, I agree with that.
Okay.
We shouldn't try and do absolute index of first element there, because then it would then shadow.
Yeah. Yeah.
Like EBS index, but maybe doesn't really feel better.
Yeah.
I think just index, or we could also do first element index, last element index.
Yeah, that's cool. That's better. We could.
You do first. Go ahead.
No, over to you.
First element absolute index would not shadow. It's kind of long there.
Yeah, I think that's better. I was thinking that too. Or first element absolute index, or even just first absolute index for the node and last absolute index for the node.
Yeah, first absolute index. Yeah, I think that's even better. Then it's not too super long.
Okay.
Okay. And then, yeah, I'm still happy with this name. It's just a different way to say the same thing. It's kind of verbose, but we're only going to use it in these two places now, I think. So otherwise, we'll just use the helper functions.
Yeah.
So this is actually nice, like this. Let's see where we're using it currently. There's just 3 places in there, and then these 2, and up there. Cool. The absolute index. Actually, we don't really need to do that twice. I guess it's fine to use the helper.
Do you think
here we do the same assert twice, but maybe that's fine.
Yeah, that's okay. I think it's even if the asserts compose like that, it's okay, you know.
All right.
Because then we fail fast, like at the first place where something is off. What do you think of only having a helper just for the last element? Absolute index of last element. Then because
the reason I had a helper for the first one was because it did the bounds check. It's just because it did the bounds check.
Yeah.
Otherwise, we don't have that.
Okay. Maybe. Yeah.
It's nice and symmetrical like this, I feel like. So here, now we got to switch on switch direction and do our 2 asserts. Ascending assert array first absolute index start node. Plus or equal to absolute index. That's the one side, then descending assert array last absolute index node, and then this is the other direction. This is greater than or equal to absolute index.
Yeah.
Cool.
Wow. And it lines up nicely.
Yeah, because we have the one off from descending and the one off from first versus last.
I've been thinking I definitely want to put this code haiku lining up stuff into Tiger Style Guide, you know. Just one or
Not
two
sure.
examples of like if it can be done, like it can make stuff nice.
It looks nice.
Yeah. Although here we were just like accidental, you know.
Yeah, I mean, sometimes there's just happy accidents like that.
Yeah.
Um, cool. So that's the assertion done. Now we need to iterate the other direction, I'm pretty sure. Should we just do a... I think we should probably just put this loop in the switch.
Yeah. Yeah, I think so too. I was kind of thinking like we'll do the whole thing in the switch.
Yeah. Because there's no really way to make this loop. It's just gonna make the loop even harder to read if we try and like do it all in one loop.
Yeah.
Okay. But should we do it in the same switch? I guess we should probably just put everything in the same switch.
Yeah.
We'll just here put like all the ascending stuff in there. It's all ascending stuff. Like we can put the return in there, I guess. Otherwise we'd have to like take the variables out of the switch. Oops.
Yeah.
What have I messed up? Here it is. Okay. It's just like the simplest way to do it. I mean, maybe we can factor the return back out. I'm not sure. We have to then basically get the node and the relative index out of the switch if we wanted to put the return in one place at the end.
Yeah.
I think that's probably not worth it though.
We
It's
could
a little
have
bit long.
what we could do is to make the control flow like maybe a little clearer is have two helpers here that we call out to through the switch.
What would our helpers be?
Yeah, just basically to return the iterator.
Yeah, it'd just be like one function that says like iterator, ascending iterator, and then
Exactly.
yeah, it doesn't really help us too much.
Just to get rid of the indentation.
Indentation's not too bad there because we now have this helper. So now we're under 100 everywhere already.
Okay, cool.
But I think we're all right like that. So that's the ascending direction. Now the descending direction. See how this works out. And we need the same thing essentially with the loop. Just copy this for now, and we'll fix all of it. So node equals start node. Now we're gonna do the other direction and say, well, node -1 is greater than 0. Actually, I think it's while node is greater than 0. Is that what it is? Yeah. It's while node is greater than 0.
Yeah.
I wonder if we should here flip it around to be array node count -1. I guess the +1 corresponds to this though, so I think I like it like this.
Yeah.
So let's leave it like that for now, I think. Okay.
Okay.
While node is greater than 0, and while well, I think it's greater than equal to 0, isn't it?
The one loop we're gonna increment, the other loop we're gonna decrement. So it can't be equal to 0, otherwise we'll have
You're right.
underflow.
Yep.
Or
And
underflow.
here, yep. Yeah, underflow. Absolute index is now, it's going to be the same check as we did in the assert, I think.
Yeah.
Last absolute, well, no, it's the absolute index is, yeah. So it's the same check, it's the other way around. Absolute index is less than or equal to, I think we should put this check the other way around again.
Yeah. Because we're checking the argument.
Yeah. Do the same one again. This one as well, probably.
Yeah.
It's greater than or equal to. Yep. So then when while this is true, and this now to be last absolute index. node plus 1. Is node plus 1 is not right though. It needs to be like node minus 1.
Or I think
Or
it's just node.
Let's think about this though.
Yeah, this loop is maybe totally different. So
It's node minus 1. This is good now though, I think. Yeah. Well, this is not really a useful assert anymore. It's just the equivalent thing would be a node greater than 0.
yeah, so that can go.
It's already sorted by the down or overflowing arithmetic checks.
Yeah.
And then relative index is going to be absolute index.
Can we step? Shall we step through that while loop again?
Sure. So yeah, we got our start node. We're gonna check if the start node is equal to 0. We're gonna break the loop. This check could actually be not equal to 0. That might be a little bit more readable. What do you think of that? Instead of doing greater than 0, we'll do not equal to 0.
Yeah. Yeah, I kind of like the greater than 0.
Okay.
So it's
Yeah,
like
but like while the node's not 0, it's essentially what it is.
Yeah.
I'm gonna step it down. Yeah, I guess that's more stating it in the positive instead of in the negative. I guess
Yeah.
it's a good way to think about that.
Yeah.
And while the absolute
also
index,
just because it's symmetrical with the ascending loop, we're flipping the sign.
right? Yeah, makes sense. So we say like while there's a next node to go to, and while the absolute index is less than the last element of that next node, go to the next node.
Yeah.
So here we definitely want to look at the next node that we'd be looking at.
So the next node. Yeah.
Yeah. So here we assert that it has to be visible from the start node, so that it would be okay to start the start node and iterate from there. Where the absolute index is less than the last absolute index of the start node. We assert that, and then we say, okay, but we might be able to put a tighter bound on that. And then we go and look at the next node, this node minus 1. We say, okay, does this tighter bound work?
Yeah.
And if it does, then we shift node.
Yeah, that's a great way of explaining it.
Cool, thanks.
Yeah.
This is correct, though, I'm pretty sure.
Yeah. Shall we do the while conditions on a single line?
Oh yeah, we probably could. It's 94. That works.
Okay.
Up here it didn't work though. It's a little bit longer, yeah.
Okay.
So we'll just leave it like that.
Oh, we could we use that same helper up top? Would that help?
Oh yeah. We can use the other one. We should be using the other one, in fact.
Yeah.
It's still only gonna fit though. It's still 114, but it's definitely a bit cleaner.
Yeah. And yeah, that's nice. Node plus 1, node plus 1, node minus 1.
Here, to make it really symmetrical, we could do node minus 1 greater than or equal to 0. It's maybe just overcomplicated things, though. What do you think about that?
Yeah, I think we might then hit the underflow if the node is currently at 0.
You're right. Yeah, we can't do that.
Yeah.
Good catch.
Thanks for trying it. It's pretty cool. Like it's a nice we're learning. I really like this idea. Like to make the different control flow, make it symmetrical if it is symmetrical, as much as possible.
Yeah. Cool. This needs to be last absolute index. Is that right?
Yeah.
No. This is still. I think this is still first. This is a this is tricky. It's still supposed to be first.
Yeah. Okay.
we want the relative index to the node. That's from the start of the node is how we've been using it up top.
Yeah.
So this is still first. That means maybe we could unify this last bit of code here and just do the node in the switch.
Yeah. Which would be nice.
Yeah, let's do that. And then this done check is this gen check's not the same though. Can the relative index even be? That's a tricky thing. So I'm gonna go back up to the calling function for a second.
Yeah.
This actually gets kind of tricky because this binary search, if we're doing like the other way around and searching for a key max, returning like the smallest key.
Yeah.
It turns like the tightest the lowest upper bound on where the key could be. Is that right? Yeah.
Yeah. It's it's the smallest, the index of the smallest key that's greater than or equal to, or so it's the index of the key of the smallest key that's equal to, if it's an exact match, or greater than what we're looking for. But I think we're also going to have like a directed binary search, so we'll switch use like comp time.
Yeah. Problem arises when we're doing then the other way around and searching for the smallest or the greatest lower bound. If you're doing like the key max binary search, which is the opposite of what we've got implemented now.
Yeah.
Because then if you're searching for an element smaller than the smallest element in the array, and you try to return -1, it doesn't work because you've got a signed integer.
Yeah.
So
then we have to change the return type.
I guess, yeah.
Yeah. So we want to just use one binary search then.
Maybe. I'm not sure what the right thing to do here is.
We could have binary search return an optional index.
It's probably slower though. You have to like branch in there then.
Yeah. Because we already do have a branch. Oh, okay. Yeah, we don't have a branch.
We got a compare keys branch, so that's the only branch we need there. Yeah.
Okay, so
yeah. So can we do it? Can we just use this same binary search to handle the maximum case as well with like a slight inefficiency?
Yeah.
Yeah. I think we should probably do that then.
And then we can just document like why the trade-offs, like we considered an optional index return type, but that would introduce a branch, or
it also allows us to keep using an unsigned integer for the return type too, which simplifies the code.
Exactly.
And reduces the way things can go wrong.
Yeah.
Okay, and so our binary search, what will we pass in here now if we're searching for, we want to find the maximum key.
Yeah.
Or we want to start at the maximum key. Or I guess we're trying to find the maximum key actually, so we can start iteration.
Yeah. Then we're gonna do key max, and we'll look in our root, because we'll do the binary search there.
All right. It's gonna give us then. And we actually want to take the next key node in the root there, don't we?
Yeah. Yeah.
So the keymin is guaranteed to be that's like the tightest lower bound on where the key max is. We actually want the tightest upper bound.
Yeah.
So we can start iteration there and iterate the other direction. So we need to take then key node +1, or if so we need to take the key node +1 here, I guess, and handle that. Or then use like the last node in our nodes if it would be out of bounds, I suppose.
I think is it not key node -1? Because we want to go to the left when we're descending.
You know, we need to make the bounds over that whole area though.
Yeah.
So, maybe we should just like draw this out real quick.
Yeah.
What was the
idea.
website called?
Whiteboard. Yeah.
There it is.
Nice.
So, say our element is here. I'm making like, do use red? Yeah, so our element's here. And let's say our nodes are like this. Something like that. These are our different nodes. So we're gonna binary say this is the maximum key, and then we can say the minimum key is here.
Okay.
Right. And now we're going to do our for the root nodes. These are all the root node keys. The root node min keys are the green lines here, I guess. And so we're going to binary search on these green lines to find the min key. Well, I'm doing the ascending case first. Then we'll find this min key.
Yeah.
I believe that will then be the greatest min key in the searched array that is less than the target, less than or equal to the target. And so that's the place we want to start our iteration. Then we'll go this way.
It'll actually be the key that's greater than or equal to. It's the smallest key that's greater than or equal to.
So it's this one.
We'll actually get that.
Oh, so we're doing this wrong right now?
Oh.
Glad we're doing this.
Yeah. Yeah. You know, remember when we did the Zig Showtime with ViewStamp replication, and at the end, Larice asked if this is always how we do our meetings, you know, with these diagrams and things.
Oh yeah, we do this pretty often when we get lost.
Yeah.
I'm just looking back at the test case to make sure I'm understanding this properly. So this is the array we're searching. These are the keys we search for, and these are the results of the searches.
Yeah.
So if we're searching for key 1, yeah, you're right. It gives us 3. It gives us the index of 3.
Yeah.
All right.
The smallest key that's greater than or
you're right.
equal to.
We did get this wrong then for ascending, or I got it wrong or something.
Oh,
so now
too.
for ascending, it's going to give us this key min. So we need to actually subtract 1 in that case then. Okay. That's all right though. And then for descending, we're going to search for this key. It'll give us this key min, and then which corresponds to this node. And then that's actually exactly the node you want to start at, isn't it? Actually, no, we want to start at this node.
Yeah.
And then we search again to find this, and then do the absolute next. I think we always subtract 1 then. Yeah.
Not necessarily. It depends on if we can tighten the bound or not. So I think that this step for the key max case, that's where we're going to use the bound tightening loop. That'll sort it out.
This is for going from the root node to the key nodes. Then we need to search again in the key nodes to find a bound.
Okay. But what if it's an exact match for key max? Then we
that's the case where we don't want to subtract.
Yeah.
So if key max is here, I should like return if it's an exact match or not. That'd be useful, but I guess it doesn't right now.
Yeah. For key min, we also can't subtract 1, because it also could have been an exact match.
Well, for that one it's fine, because we then end up, so if keyman was here, we subtract 1, we'd end up here.
Yeah.
And then it's not in this node, so we wouldn't find it.
Yeah. And maybe we had an exact match. I don't know. I'm kind of thinking we should just do an optional index and
Binary search.
yeah.
Yeah, instead of doing I think that'd be better. Well, would the optional indicate exact match or out of bounds? Yeah, I think it would be like returning a bool for exact match plus an index.
Yeah.
Something
So
like that.
that doesn't help us too much.
That would compare keys to see if it's an exact match.
Sorry. Excuse me.
I think that fits in our current API though. We can already just do a second comparison to see if it's an exact match. If it's not an exact match, then we go to the previous node and start iteration there.
Yeah. Okay, cool. So if it's not an exact match, we subtract 1. If we're not at 0. Yeah.
And if we're searching for this key, well, we'll find this. The only case where we find where we would end up getting this node is if we search for this exact min key. We don't actually need to handle that special case. We'll never find. Actually, we'll search for keys outside the bounds of the array sometimes. You're right.
Yeah, either side. Maybe what we could do is actually put this into comments later, so that we've got these little examples as comments to show like how it works.
Yeah, we probably should. Yeah, I think this does work though. We don't really need a separate binary search for the max key or the max key search. It's the same thing basically.
Yeah.
It may actually unify more of the code if we don't have that separate case.
Yeah, it's quite nice.
Seem like it's inefficient. The other way around would just be like, we would have then the mirror image, so we'd end up getting this key, and then adding 1, or, well, these would be max keys. It doesn't make any sense to do it that way, because these are all min keys that we have in our root node.
Yeah.
And so if they were all max keys, then we would end up getting this one, like, or, I don't know, maybe this one, and then subtracting 1 to get it to there. I think it makes sense to just keep keys though.
If we did have 2 different binary searches, we could get it right, so that we don't have to subtract 1 or do an extra compare. We just have to swap it around which one we use.
Oh yeah.
Then we would
I see. We would do like the max search for the minimum key and get like the min key that's less than, or the greatest min key less than the key we're searching for.
Yeah.
So the max is actually perfect right now. Are we getting the thing we want?
Yeah. For max, we're gonna get the one on the right hand side.
We get this exactly. Yeah.
Yeah.
And then we actually just want to start. Well, we actually want to go to this node, then and do another binary search there to find the key.
Yeah.
And then once we find that key, well, or not find that key, we still start iterating exactly that place.
Yeah. The one challenge with having 2 binary searches is we come back to then maybe we need an optional return so that we avoid the out of bounds or using us.
I'm not sure we need that or not. I think what we want is to do a second comparison of the keys to see if their keys are equal.
Okay.
But I don't know, can we get around that? So in our binary search currently, we finished off with this compare keys. So we can get around this. So if this compare keys returns true, so it's checking if it's greater than or equal to. That's what it's checking.
Yeah.
No, or if it's not greater than, checking if it's less than. So not greater than or equal to.
Yeah.
And then in that case, it adds 1. We don't actually know if it's equal to or not here.
Yeah.
In the case that they are equal, it won't add 1. Yes, that actually does make sense, because we've now gone through here. So we could here, instead of checking less than, we could check if they're not equal.
Yeah.
We'd still pass all the tests then. And we could then like return a second value that says if they're equal or not.
Yeah. It would introduce a branch because we would not be able to use bool to int.
We could. We could
Okay.
do something like this. We could do const equal or exact match equals this. EQ, and then here we would do bool to int of not exact match, and
Okay.
that'd be the index. We then like return a little struct that says dot index
Okay,
equals
cool.
this,
Yeah.
and then dot exact equals exact match.
Yeah.
You want to call it exact or exact match in this struct? I don't really have a strong opinion there.
I think exact is cool.
Cool. I'll make that seem consistent here.
Yeah.
And then we get a return type.
That's pretty
on
cool. Yeah.
Search result. Or binary search result.
Yeah.
We won't really ever type this type, so I'll just make it kind of verbose.
Yeah. It could even just be called result because it's within the binary search namespace.
Well, it's inside our manifest level namespace right now, but
okay.
it will eventually be inside the binary search namespace, and we can rename it then.
Yeah. Yeah.
Cool. I think this does it though.
Yeah.
Just need to make
So
the type.
this is I need to run, and maybe this is a good place for us we can pick up tomorrow. What do you think?
Sounds good to me. Yeah, I guess I'll just do some more another WIP commit to just start changes online, and then keep going with this tomorrow. I think we're close to like doing an actual pretty beefy commit though, and say like manifest level stuff is.
Yeah.
We got the read path implemented. We can do a commit after that, and then we can do the write path another commit, and then start tying it up.
Yeah. Yeah. It's going to be awesome. Really nice. Yeah.
Cool.
Cool.
Right.
Yeah. Looking forward to tomorrow. It's been a really fun first day. Pair programming.
Felt much more productive than I thought I would be, but
yeah. Yeah. Adjusting to the new time zone. Yeah.
Yeah.
Cool. So I'll sign us off. Yeah. Thanks, Isaac. Welcome back, and really, thanks everybody for joining us. It's been great fun, like seeing you around. And feel free to chat tomorrow. We can maybe see who's all out there. But it's been pretty nice seeing you guys pop in. So yeah, Tiger Beetle sessions, session 6, Wednesday, 12th of January 2022. Happy New Year. Cheers, Isaac.